the store fronts are all empty. The stores
Yeah,
are empty
exactly.
and untended, so they're in disrepair and
Yeah.
you know no jobs.
No jobs, exactly. It's horrible.
Yeah, but the army brought me to Georgia. I had to join the army to get through medical school
Okay.
because of financial factors.
Of course.
And so then I owed them a few years, and they assigned me Fort Gordon, Georgia. It's funny because I there were they gave me a list of 20 places to rank in order of my preference about where the Army would assign me,
Right.
and I put Georgia as third from last. The
Okay.
only ones that I
Of
put at
course.
lower rank than Georgia, one was, I think it's called Bremerhaven, Germany, and the
Oh,
other
yeah,
one
yeah.
was somewhere in South Korea. And so
Wow.
I put Fort Gordon, Georgia as third from last of the 20. And I figure there's some guy who sits in an 8 by 8 foot cubicle in the Pentagon with no windows and chuckles as he assigns everybody his last choice. You know what I
Right,
mean?
exactly. Well,
Oh, hey, that's
that makes
last
perfect
choices are
sense.
good for military discipline.
Exactly. Yeah, I was in the Navy, so I went to, that was one of the reasons I went into the Navy was to get the GI Bill. So,
Uh-huh.
and I had gone to college for like 2.5 years and had majored in biology, and, took all those courses in chemistry and whatever. And then I went in the Navy and I was an air traffic controller, served on an aircraft carrier for 3.5 years. And, but that was good. It was a good experience. So,
Well, I actually, so I am in Georgia in the Army, and
yeah.
I actually decided that I liked Georgia.
Okay. So you
So,
stayed.
yeah, and I just made a lot of friends, and some of my colleagues invited me to join them in private practice, so I did,
Okay.
and it worked out well. I lived in Augusta for years, 25 years, 27 years.
Okay.
And then I decided I wanted to work in emergency rooms in rural Georgia just
Okay.
because there were good opportunities. And I moved to rural Georgia. So now I'm out in the middle of nowhere. And people ask me where I live. And I say, I don't live in a place. I just live out in nowhere. No neighbors.
That can be
So,
fun.
yeah, dark sky.
Yeah.
And I still tell people I live in the darkest spot in Georgia, and then I
Yeah.
tell them jokingly that it's darkest from the moral standpoint, not the scattered light standpoint.
Right. Right. Right.
But don't believe anything I say.
Well, I know it's that can be tough. I grew up in southeastern North Carolina. It was like
Uh,
I grew up in Hope County, which at the time was one of the two poorest counties in North Carolina. And I mean, when I was growing up, they still had outhouses, So, and some of the people were still living in shacks. So it was like that. But my mother, she was an RN, and one of my aunts, she was the county social worker nurse, and so they did all that stuff. So, but later on, I worked as an orderly. Remember the orderly? Get the orderly.
oh
But
yeah.
when I was in college, but it was a good learning experience. I've worked in ER, triage and catheters and all of that stuff.
Catheters, that brings memories back. I always hated intubating people. But Venflon's not a problem. The most needle phobic guy available. I can distract him long enough to put a Venflon in his hand and take
Right,
it.
right.
But getting somebody to calm down and let you intubate,
Right.
can that happen?
Yeah, that's hard. That's hard.
Well,
I used to be
I've
an
done,
ex-paramedic. That's why I remember these things.
in the ER, I probably averaged one intubation a day for 24 years. And I called someone for help once, you know. In other words, Let's get an anesthesiologist. I just can't do this one. I've done a lot of them that are difficult. You develop a skill.
Yeah.
And one time, only once did I have to do tracheostomy.
Well, diver medic in the North Sea, you are taught how to administer morphine.
You're right, right.
And I remember going into a big department store here in the UK.
Wayne Bailey, Lunar, David Teskey, Messier, Frank, Catching the Air Star, Greg Shanos, the SeeStar 315. So that's the first one that I'm really interested in.
Oh, I'm interested in all.
I asked for
I
a
don't know
certain shade of lipstick, and the girl says, "What do you want it for?" And I looked her in the eye and says, "I work in the North Sea as a medic, and I am going to write the letter M on their forehead, like you're supposed to when you use morphine." And she looked at me, her jaw dropped. "What color was that again, sir?" Something red. Okay, I'll go get my supervisor. Having said that, it being a waterproof one, it was brilliant. And I used it 3 times. I was so happy it was only 3 times, because the paramedics in the UK do not like offshore medics giving.
Yeah.
Doctors, they're fine. You got paperwork? Yep, here's the paperwork. But the paramedics used to get very upset. "What did you give him?" I said, "I'll give him X milligrams of morphine," and that was 4 hours ago.
Right, right.
"Why are you doing this?" That's what's in. That's the only thing I've got available in the lockbox on the rig. You're not supposed to. I said, "I have been trained to give it. Here's your patient. Here's your paperwork. Now kindly shut up and let me go."
There you go. That's
Oh well, such is life.
Yep.
Oh, hopefully this weather will break. It's been 24 degrees Celsius all day,
Wow.
and I have
Is that
been
hot or cold? 24 Celsius.
hot.
It's hot.
Oh, goodness.
We abandoned Imperial in the UK years ago.
Yeah.
Well, let me think. Our temperature was 105 Fahrenheit for a day last week. I guess that's about that's 42 degrees Celsius.
We had 30, 31 last week. Today was 20. So great.
24 Celsius is 75.2 Fahrenheit. So that's nice and cool.
Yeah.
Yeah, it's 30 degrees Celsius here today in New York.
Yeah, about.
That's in the 80s.
So I'll be staying in today.
Most people in the UK don't know what the term AC means.
Yeah.
I live in upstate. I live in Capital District, New York.
Right.
I've been there over 40 years. I have never, ever had an AC in the apartment.
Right.
Don't even run it in the car.
Yeah.
Just crank the window down, get a breeze as you're zipping up.
Right. See, I like that. When I grew up in the country, you could open a window, sit out on the front porch or whatever. You get a breeze, that's nice. But in the city here in New York, you get these bad air days. So you really have to shut your windows and, and it's hot. It's just horrible, You have to have an AC here, so.
I'm in Cohoes, New York.
Yeah.
And I am about 800 yards from the Hudson River.
Yeah.
And 300 yards from the Mohawk River.
Okay.
Which is really good, because for imaging purposes, it means that the river does an awful lot of good work for the actual air quality and stuff.
Right.
Does everybody?
New York City. New York City is a domed city. A lot of people don't realize this, but if you drive out to get way out on Long Island, turn around and look back at New York City, you'll see this gray dome over it.
Yeah,
And I'm talking about smog.
yeah, it is. That's exactly right. Yeah.
Yeah.
Well, I go from JFK to Jamaica, Jamaica via the LLIR to Penn, Penn to Rensselaer. So I really don't see much of the city.
Yeah.
And considering the fact that if I've got off a flight, I'm not really in the best states anyway. I drove from Boston to Cohoes. That wasn't a problem.
Right, right.
I-90 all the way. Love it.
Yeah, I don't like flying myself.
I love it.
Yeah.
In fact,
I'd rather take a train or something like that if I have to travel.
but I miss the old days when I used to wake up somewhere and say, what week is it? Oh, that's where we are. Those were fun days. We always flew by turboprop because we flew with our kit.
Right.
And okay, the advanced party went ahead. They flew on the jets. That's okay. Good luck to you. I'm going to sleep properly because by the time you get to operational ceiling in a turboprop, it's smoothed out and it's such a longer trip that you wake up and you're more in sync. But everybody's so busy. We have to be there urgently, almost yesterday. But,
Okay.
bad news about Ryan and me. But ho hum.
Hello, everybody. Anybody can hear me?
Yes, Frank.
Okay, good.
How
How's
you
everything
doing?
going?
Good.
All right.
Hey, Gregory.
Hello. Who's
Hi.
that?
Julian.
Oh, hi, Julian. Why does it say Parks?
I don't know, but that was it just says Parks.
Oh, okay. Did you get my images of Saturn, the transit of Titan?
Yeah, I receive it. Yeah.
Yeah. No, Julian, you must.
Okay.
Yeah. Did
I
you
don't
get
think
it?
so. No, I don't remember getting this. No.
Really? I put it on the HST Jupiter groups,
Oh, okay.
and I had yours on it too. Oh, all right, because I have 13 images from Titan just touching, going all the way through.
Right.
So
I haven't looked at it. Maybe that's why I haven't seen it.
All right, I'll resend it to you after.
All right.
Frank saw it, and he was imaging too at the time.
Yeah, there's another one coming up Thursday morning, August 1st.
Yeah.
I think this time Titan was skimmed right along the southern edge of the limb. Okay, so I think that's going to be the last transit for until the rest of the year. So the ring is open up more, and the orbit, Titan orbit, they're going to open up too, and it's going to go north of south of Titan, Titan north of Saturn. So it's going to miss us for the rest of the year. So I will be at Telephane that morning, so I won't able to see it.
Oh, you're gonna be a Stellar fan, okay.
Yeah, Telephane starts next weekend. Yeah. So I'm going up there earlier.
How's the light pollution in Stellafane, Frank?
With that,
How is the light pollution there since they put a prison nearby?
oh yeah, they would, yeah, there's a prison camp not too far away. I don't know. It's a very little light pollution. You get some light from the town of Springfield. Then you see some glows in the distance, but I don't think it affect that much. So,
I went up a few times after the prison, and it really, I think they did a pretty good job of trying to ameliorate that. It's still fairly nice. Certainly a lot nicer than the Baltimore area.
yeah, it's
Yeah.
not dark it used to be when I first went up there back in the early 1980s. I remember the sky was much darker, but it's still not too bad. But it's not the darkest spot in the Northeast anymore. I think Cherry Spring in Pennsylvania, I think it's the darkest.
Have you ever been to North South Lake, Frank?
No.
It's pretty good up there. Also, the Ashokan Reservoir Dam area. It's very dark.
Okay. All right. Mainly I just go to Stellafane. I'm not really going in a lot of star parties.
Right,
I
right.
think, I think about going to Cherry Spring, Pennsylvania. They have Cherry Spring and Black Forest.
Right, right.
Star party. So I'm gonna get a chance there. The only problem is that they have very few hotels accommodation there.
Right, right.
I don't camp out.
You have to slug it out.
Yeah,
I don't mind that. I love it.
yeah. So,
I was just Eric Jones, estimating gradual number of technologies on the graduates.
Hey, Howard?
Hello, how you doing, Frank?
Okay, yeah, I observed the sun this morning.
Good for you.
Yeah, did you see it? Did you observe the sun this morning?
There was a hole in the sky to the north, but none by the sun, and it just got worse and worse.
Well,
I got to
okay,
see it
yeah.
yesterday.
Yeah, okay, yeah. It's a nice group of sunspots. It's like line up. That's like
Yeah,
the
that's
first
really
again,
neat.
then line up. Yeah. They
Almost-
would through the H-alpha filter. It's not much going on. But, it's just not too many prominents around. So
It's still fun to see.
yeah.
There was a lot of spots.
Hi, hello, everybody. Hi, Tim.
Hello.
Hello.
Hello, Ken.
Okay, everybody, welcome to Fantasy Island. The aLpo conference. So, should we do a pop quiz and ask anybody what they learned in school yesterday? No.
Not if you want people to stay on.
All right. A couple things. First of all, thanks to all of you who did presentations yesterday. They were really top notch. And I'm not just saying that. I learned a lot myself. I was especially interested in Bob Garfinkel's talk about what you could consider for your aLpo style library. And, Bob did a really great thing, and as well as everybody else. That was really good stuff there. I'm going to repeat this thing from yesterday. I don't know how many of you are t-shirt people, but I have a t-shirt that I bought at an aLpo get-together many years ago. And on the back is the aLpo logo. Now it's faded. I don't remember which conference I got this at. And I remember asking, I think it was John Westfall, and nobody knew where it came from, who handled them.
Mhm.
Are any of you interested? Because if so, I would put forth, I don't know if it'll take a motion, but I would work with the board on and getting a quantity of these things because they are so cheap now to get. I don't know, I would guess they're probably going to be $8, $9, $10 a shirt or something like that. We're not looking at making money so much as we are promoting the organization. Are any of you interested in an aLpo t-shirt?
Yes.
Yeah, they all come in different colors or what?
No,
Or
right now, well, I could look into that. I mean, I would look into that and then do a group email to everybody. But right now, let's just assume for the sake of this discussion, are you willing to wear an aLpo t-shirt? And if it's not cost prohibitive, I mean, we're not talking $20 here. We're talking a lot lower. Would you be interested in getting one?
Oh,
Yes?
yes.
Okay,
I would.
yes.
Yeah.
Yes.
Okay. 'Cause
You might even put on the bottom
Very much.
watchdogs of the solar system.
Yes.
I mean, somebody's got to do it.
Exactly.
We're not getting any help from anybody else. I myself, I'm not a ball cap wearer.
Me either.
You know, I don't like hat hair, cap hair. You know. Okay, and before I get into anything else here, I've got something I want to ask those of you online. I've got a Celestron power tank, and this is the doodad that connects it with my Celestron AVX go-to mount, which I'm very happy with. And being the good neighbor that I am, at an observing session for a local astronomy club that I attended, I lent this to another guy, a really nice guy, but I forgot who it was. And I even forgot that I lent it to him for months. And when I got it back, lo and behold, I don't know if you can see this, there's no
Yeah.
central. It's missing.
Yeah, exactly. Yeah.
It fell out. It's either in the grass at this big observing field or it's long gone. I contacted Celestron and they really came through and they sent me another one of these. But being the kind of person who waste not, want not, I'm willing to pass this along to somebody who could find the doodad that goes in there. And it's yours. It goes with the Celestron power tank to an AVX mount. At least I know that. Is anybody interested?
I'm good, thanks.
Silence is golden, huh?
Yeah.
Yeah, Ken, I could make use of it.
Steve. Steve?
Steve.
Okay, you're local
Yeah.
to me, so I could get it to you.
Yeah,
Okay.
I'll see you sometime soon.
Yes, sirree.
Thank
All
you.
right. Let's see. A couple more minutes to go here. A little bit about myself. Those of you who don't know me, most of you do. Originally from Cleveland, Ohio, moved to Atlanta to move from general mainstream journalism publications editing into technical writing. And I took a position with a local company here. It's now long gone, but that was in 1984. They made computer peripherals, plug-in memory boards, accelerator cards for PCs, XTs, and the brand new thing called the AT computer. And so I wrote the user guides that came out with the Quadram products, their multifunction cards and stuff like that. Went on to an extended career writing factory equipment manuals and heavy construction equipment manuals for Komatsu and other companies, but always maintained my passing interest in astronomy. I rejoined the aLpo in 1990, I think it was. It was like meeting a newfound friend because I gave up on astronomy back in 1966 when I was in high school. And so much had happened and developed. There used to be refractors and reflectors, and now there were Schmidt-Casses and all kinds of stuff. So I got back into astronomy and joined the aLpo and the local clubs. Bought a Criterion RV6 that I held on to for many years. And I will never be the observer that many of you already are. I know my limitations, home duties and things. I'm not dumb, but I just I'm just not going to be as good. I'm still getting out there when I can. But my talent is in communications and writing skills. And so it was in 2001 that the late John Westfall asked if I wanted to go ahead and assume editorship of the aLpo journal, affectionately known as The Strolling Astronomer, which I am told got its name way back when Walter Haas started the organization. Rick Hill, you've known Walter a long time.
Since 75.
75. I understand that it got its name because when they were starting it off, they had I'm not sure it was a house cleaner or a maid or somebody or a secretary.
No, it was actually Eugene Foster who helped him construct the first mimeograph copy. Eugene Foster had a background in advertising and promotion and was studying at the University of New Mexico, Albuquerque at the time Walter was teaching there. I talked about this in one of my presentations a few years back.
But I was told that the name Strolling Astronomer came from the housemaid or...
No, that's not what Walter said. He documented it in an article.
Okay. So there you go. So we call it both. We call it Strolling Astronomer,
Yeah.
we call it the Quarterly Journal, but it's, and if you get it as the hard copy, it's the JALPO, Journal of the aLpo. If you get it online, it's the DJALPO, digital version of the journal, and so forth and so on. So I was able to use my editing skills, and I tried to make every issue at least a little better than the one before. And when I look back at my first attempts, I cringe, but I did the best I could. And I believe that the idea is to not just publish papers in manuscript format, but to make them somewhat eye-catching and something that people would want to look at and want to read. And I think I've done a good job. I've gotten compliments for my work, but it remains to be seen if my work has really succeeded in gaining or holding on to membership. But that's what I do. And when I can get out, I do some imaging. The only imaging I've done was with the old Meade LPI back in 2003. Did some lunar imaging. I was really happy with that. That was when webcams were brand new. I think its only competitor was the Philips 2 UCam, and so forth and so on. A few years ago, because this job does take so much of my time, there's not 3 days that go by when I'm not putting in several hours on the journal. And I remember asking some people to help me out, would you do an article on this or that? And they said, well, I'm too busy. Well, here I am. So I somehow got in touch with Sean Dillis. I don't know if he's online. I put a call into him this morning to ask him if he could be here, but Sean is in the Washington, D.C. area. He's retired as well as I am retired. And he has been a godsend to working with me. I kind of gently guide him, but he does the reminder emails to the rest of the membership about getting papers and presentations ready for the journal. I think the next one we're looking to get, if you've, all the section reports and everything, please get them to me, let's say by the end of next week. But the notice originally went out some weeks ago, so this is not a surprise.
Yeah.
And Rick Hill, don't worry, we did have a short deadline, but as you know, I said we corrected it, so it's not July 1st, but around August 1st.
Yeah.
We're going to go with an extra week. The plan is to get the next journal out, and I always try to get it out seasonally, the beginning of the seasonal month. So if the autumn season begins in mid-September, I would like to get this thing out by the very first part of September, because the digital online version will be immediately available, but the hard copy will go to Sheridan Press. They process it, they mail it, and by the time it gets into the regular mail boxes of those who get it, it's near the end of September, generally speaking. So, I want to thank all of you guys. Is Pam Shivak here?
Ken, how many people actually get a hard copy?
Matt? You're muted.
About, I would say currently around 145 members.
That many?
Yeah,
Oh.
it's roughly a 40 to 60% split. 40% get of their membership gets the hard copy journal, and almost 60% gets the digital journal.
Right.
How many of those go to institutions?
Not many. I would say less than a half dozen now. We used to have more institutions that would pick it up, but the problem with university libraries is that they tend to, when they want to cut back on budgets, they tend to identify ours more as a hobbyist publication than a scientific journal. So that's usually the first things that get cut by a university library, unfortunately.
Right. I don't see, and I would fight vehemently to not abandon the hard copy of the journal, whether it's black and white inside or color inside or whatever. I grew up loving to read, whether it was magazines or books from, very young elementary age on. I worked at a public library in Cleveland, Ohio while I was in high school. It's going to sound kind of stupid, but there's nothing like the smell of an old book when you open it up.
Yeah.
But in any case, we will always publish the hard copy. Maybe, and I'll probably consult with Matt on this. I've toyed with the idea of trying to write. We don't have to discuss this now, Matt, but I wanted to talk about doing perhaps a grant request from the National Science Foundation or whomever. Maybe we would get a chunk of change to possibly do color inside pages, but that's something that we'll talk about offline.
Okay.
Anyway, in a nutshell, that's it. The journal comes out quarterly. Our page count now exceeds that of Sky and Telescope. We have 2 very loyal advertisers, that being Celestron and Sky and Telescope, a la American Astronomical Society. And in the past, we've had a few other advertisers that have dropped off. I don't think we'll ever have Mead again because Mead ain't around. Let's see if there's anything else. I'm sure I'll think of it later. Does anybody have a question about the t-shirts, about the cord, about the journal, about me, about Sean? Okay.
You're doing a great job, Kim. That's all I want to say. This is Richard.
Yeah.
I am struggling a little bit with reading the computer, so I'm glad that we're going to keep a hard copy.
Yeah.
I've actually had to move my screen up closer to me, and I don't know. Maybe it's something called old age. I don't know.
Well, in my case, it's memory. And I'm not in dementia, but I will tell you that I am very concerned sometimes about, I just had this in my hands, I put it down and I'm over here. Where the hell did I put? And I've talked to my primary doctor and was told, no, at my particular age, which I'm 74 and a half. No, this youngster, this is normal.
I'm 86.
I'm having a hard time accepting it. Who's 86?
Me, Miller, with the sun behind me.
Hell of a spot you got there.
Yeah.
Well, I hope to at least reach 86, if not later. But and by the way, Chuck Wood, I talked with Chuck on Wednesday afternoon. Charles Wood does the lunar photo of the day, which is now really a repeat from what used to be on. They don't do brand new ones, but it's still a great. Well, I have it set as my sort of homepage when I open up my internet as the landing page. But I talked to Chuck because he's a member of the International Astronomical Union, DIAU, and he's in the I forgot the exact title, but it's in the nomenclature section. And we talked about naming features for particular members deceased of the aLpo and so forth. But Chuck informed me when we were talking that he actually had passed away for about 26 seconds not long ago.
Ooh.
His heart stopped and They brought him back and he's fine. He did not know that he had an undiagnosed case of AFib, irregular heartbeat.
Right.
So now he's doing a pacemaker. So it
You
all,
gotta do you got to do the therapy, Ken.
well,
You
maybe,
know, keep yourself active, you know, mentally.
yeah,
And walk. Walking is one of the best things you can do.
lifting a C11 helps out too, doesn't it?
Oh, sure, sure.
Yeah, that will.
Okay,
And do you
well,
mind if I make a comment in support of one of the advertisers in our journal?
sure enough.
There's a little company called Cat's Eye Collimation that advertises regularly in the journal.
Yes.
And if you look at the bottom left corner of their ad, they sell a eyepiece and accessory box.
Oh,
I bought
yes.
one of, and you know, my wife is a casual stargazer, and I bought one of those fancy boxes for her, and it's wonderful. She's absolutely delighted with it. Holds her eyepieces, and it's all carved with the images of the planets on the outside, not pictures, but carvings. And it's just really a delightful little thing to get for somebody you know who's a stargazer. Yeah.
It's
So I
not
just wanted to say that it's a nice thing.
right. This is not just plywood on some 2x4s. I've seen
Yeah.
one or two of those cases at a local star party, and it's very well done. It's stained. It's done. It's beautiful.
Yeah.
Absolutely.
And all the Cat's Eye Collimation stuff is really good.
So
I just wanted to say that.
So I'm urging all of you to consider Celestron for your next purchase, whether or not you buy something, but please put them at the top of the list for consideration. If it has anything to do with Sky and Telescope magazine, I urge you to consider a subscription now. They recently changed their subscription method. If you belong to a local club, it had been that the subscription rate for Sky and Tel was, I think, something like $33 or $34 a year. Well, that is no longer true. The hard copy subscription rate for Sky and Tel, if you're a club member of whatever kind, is something like $45 or so. And the online subscription for Sky and Telescope is something like 37 or 38. So that's what I myself am getting. So every month I get a reminder, just like with the aLpo journal, I send out a reminder that the new journal is available for you to download and so forth. And that's what I get from Sky and Telescope, that there's the new issue is available and so forth and so on. So I'm saving at least $6 or $7 or $8. So those of you who subscribe might consider going to an online subscription only if money is a little bit of a problem. But consider Sky and Telescope. I've been asked to approach Explore Scientific, which I plan to do. And Wilman Bell, who is also now owned by American Astronomical Society. I'll approach them as well. We'll just have to see how it goes. So before we get into the first talk, any more questions?
Yeah.
Yeah.
This is Richard. Ken, is Wilman Bell still in business? I thought they went out, but I guess
they're still around. They're owned by AAS as well. AAS/Scientel. I don't know the exact thing, but you know they are still around.
Okay. Good to know, Ken.
Okay. Okay.
Yeah, Ken, I have one question. I don't know if anybody know what's going on with the situation between me and Orion Telescope Center. Are they going out of business, or they cut down, or what? Anybody?
There's rumors that they either have just cut their brick and mortar system out and they're strictly doing online. There's another rumor that they're kaput. I don't know. If anybody else knows better, you're welcome to say so.
Yeah, okay.
And the only way to find out is to put an order in, Frank.
Yeah, I hope you get it.
Find out if it says this address. Maybe you'll get a, what is that called on the screen? A 400 error. This page cannot be found.
Yeah.
I don't know. I think the website is still up. I think.
I know they eliminate a lot of employees and all, but I don't know this. They went bankruptcy. I don't know. I know. I hear different things sometimes. And
I've read someplace that 2 Tuesdays ago, they released the entire staff. But then I don't know any more than that. So, like I said, buy something. They probably have a lot of inventory to get rid of one way or the other. Okay. Our first speaker of the afternoon. And even though I went over, I'm going to go ahead. Wayne, you're going to have your half hour. Wayne Bailey is the former, well, we call it the Lunar Section Coordinator, even though that is the one section that technically does not have an overall coordinator because it is composed of various programs, lunar programs. But we consider the Lunar Topographical Program Coordinator the section coordinator. That's just the way it is. So Wayne lives about 30 miles southwest of Tucson, Arizona, most of the time, but he spends about 2 months of the year back at his hometown of New Jersey to visit relatives. First got interested in astronomy in 8th grade when a teacher gave him a magazine article on how to build a Newtonian reflector. We've all seen those that he did with what he calls mediocre results. Wayne got seriously interested in solar system astronomy with Comet Hyakutake in the mid-90s and focused on it, that interest of comets, I guess, after retirement and moving back to New Jersey's bright skies. His main interest has always been spectroscopy, but also included just about everything except deep sky faint fuzzies. He says while he was lunar coordinator, John Westphal suggested that polarimetry would be a good topic for observing, a suggestion that he initially disregarded, but remembering the difficulties of stellar polarimetry from graduate school. So he decided to try it since he couldn't find many solar system results in the literature except for asteroids. So without further ado, I present to you Mr. Wayne Bailey.
Thank you. Thank you, Ken. Those mediocre, when I said mediocre results in the telescope, that was a generous evaluation of it. There was a later one that worked out better. Let's see, let me try see if I can figure out how to do screen sharing now. Let's see. I want to do that because I still want to be here.
Tim will walk over
Share.
to you and help you out.
Let's see.
Are you in Las Cruces today?
Can anybody see my screen now?
Yes.
PowerPoint presentation?
Yeah, just hit presentation.
Okay, yeah. Just have to do this. It should come up there. Okay.
Tim, do you want
You want to hit the slideshow tag at the top, the slideshow tag, and
how
it'll
do we
make
get
it
rid
full
of that?
screen.
There. That's a little better. That didn't what I want to do. That didn't do it. Let's see. See if it works this way. I don't know how to get rid of that tag at the top there, but it won't bother anything.
Usually if you just click on from beginning, that's the leftmost of the things. Notice there's a
Can
little
you-
green arrow on it. You want to click on that little green arrow.
There isn't any little green arrow.
The top left.
The top left.
It says
from beginning, and there's
right
a little
under the
green
heart.
arrow.
I already did that. Can you see that? Can you see the screen with it?
Right under where it says home.
Pardon me?
On the top of your screen where it says home, directly below that, you have from beginning.
I already clicked on that one.
Do it again.
Do it again.
Let's see. I've got to get out of this then. Let's see. No, it doesn't want to get out of this at all. Let's try starting the sharing again.
you're in the right screen with the PowerPoint. You just need to click on the little green arrow where it says from beginning in the upper left.
Can you move your mouse, Wayne? Because we don't see the mouse moving.
It's on the center on the slide there. Let's see.
Tap escape to see if it frees it up.
Tap a what?
Tap escape to see if it frees up your mouse. We don't
I
see.
did that a minute ago. My mouse is moving. I don't know.
No, we don't see it.
What can you actually see on the screen?
We see the main picture and then the stack of your future slides on the left. We just want to get to the
See
presentation.
your title slide, your title slide, experiments in lunar polarimetry, but we also see all the PowerPoint.
Okay, that's not what I'm
stuff.
seeing on my screen. That's the problem.
Why don't you unshare and then share
Yeah,
again?
that's what I want to do. Let's try sharing again. PowerPoint slideshow. Let's see. Let's see. Now that's what you said you were seeing.
Okay, now click from
No,
beginning.
From beginning, that's what I did before.
And
Okay, that. Can you see a slide that says introduction?
well, yeah, that's
we
in the
don't see.
stack.
That's your second slide. We don't see the slide that says introduction. We see the first slide that says experiments in lunar polarimetry.
Okay. For some reason, what's showing up on my screen is not showing up on yours.
It could be that when you do the share, you have to share your entire screen, not just the one that says PowerPoint.
Yeah.
So if you, again, unfortunately, stop sharing. And when you go to share this time, I think it's in the upper right-hand side that it'll display. When it says share, and then you get a whole bunch of different apps or screens that you can share. Pick the one that doesn't just say PowerPoint, but I think it says screen.
I got the screen that says entire screen.
Entire screen, that's what you want. Go with that.
It's showing Jim Toomey on there.
Now try again with your from beginning. There we go.
There you
When
go.
your current, oh yeah, you got it. Okay, you got it. Yeah, your
Okay.
current slide. Okay.
Yeah. Okay, the introduction. I'm going to talk about polarimetry of the moon. And this is a little bit of a new topic for me. And it's basically an experiment. So keep in mind, I'm not trying to produce scientific level results now. What I want to know is whether or not there's anything to actually see, whether I can actually do anything at all. So first, to provide some introduction. Light itself, there's basically four properties, particularly if you look at it from a wave viewpoint. Some of them are a little bit harder to explain and to visualize it as photons, but if you look at it as a wave, the direction of travel, which is astrometry, the intensity, the brightness of the light, which is photometry, the wavelength of the waves of the light, which is spectroscopy, or the color, and the plane of vibration. If you picture the wave vibrating in a plane, whatever direction that's vibrating, that's polarimetry, measuring that. Now, if you picture looking down the light wave coming at you, you'll see the wave vibrating, say, up and down in some particular direction. That's whatever direction it's vibrating is the angle of polarization. Not all of the light necessarily is vibrating in that particular direction from that object. The degree of polarization tells you how much is vibrating in that direction compared to the direction of minimum polarization, direction maximum to the direction of minimum polarization. These may become clearer later. That's linear polarization. That's the kind of polarization you probably normally think of. It can get a little more complicated than that because for any particular object, the the angle of polarization could be rotating. If the light is unpolarized, if it's the same vibrating in all directions randomly, but the angles continuously rotating, you get circular polarization. If at the same time the degree of polarization is varying as it rotates in synchronization with an angle, it'll be elliptical polarization. So the linear is a specific case of elliptical polarization. Circular polarization is the other extreme. And I'm only going to be talking about linear polarization today. So you can forget about the complications of circular polarization, even though circular polarization can be very important for some measurements, particularly magnetic fields. One of the main features in astronomy is that the degree of polarization, the amount of polarized light, is usually extremely small for astronomical objects. Usually in the range of single percent. So the accuracy in measurement is very important. This is what makes it particularly difficult. And as for what causes polarization, which is basically what we'd be interested in ultimately, to see what information about the object we can get out of it. For scattering, that's the main cause of polarization in a lot of cases. Whatever it's scattering off of, the particle size, the shape, orientation, index of refraction, all determine how it scatters light, how it polarizes the light. Reflection can do the same thing, and one of the common examples of polarization is reflection off of the hood of your car when the sun's in front of you. Polarized sunglasses help to eliminate that. The reflection polarizes the light. To give you an idea of how small the differences are, this is images of Copernicus on the moon, taken with a linear polarizer set at 45-degree increments. What we're looking for is the difference between those images, the intensity difference. I seriously doubt that you can see the intensity differences by eye. That's simply for information. In order to measure the polarization, for linear polarization, we need minimum 4 measurements. Basically, you only need 4 measurements. The linear polarizer set at 0, 45, 90, and 135 degrees, the 45-degree increments. That combination will give you all the information about the polarization. You can even get the circular polarization out of that if you want to. For the experiment here, I used 4 different linear polarizers and a filter slider, mainly because I had them. It was the easiest way to do it. We'll talk about what the best ways are, maybe later, what the difficulties are with this. Take successive images through each filter, and you should have flats and bias and, if necessary, dark images for each filter. For the flats, I used an electroluminescent panel at the telescope that I also use for photometry. For the moon, the exposure is so short, the dark current's essentially 0. And that's where I wasn't thinking things through entirely, and I didn't take bias images. Because the camera actually adds a bias to each image to keep things from going negative. I should have done that. I'll point out later what effect that has on the results. It makes it difficult. It doesn't make it totally impossible. It doesn't make it impossible to see things. You can actually see the results. Quantitatively, they wouldn't necessarily be right. There were no processing on the images except for quality selection, alignment, and stacking. No wavelets or anything like that. No image, no resolution and incrementation. This technique, I chose it because it's easy to implement. I had most of the equipment. For for feasibility test, which is what I'm thinking of this as, and what possible improvements there could be. We'll discuss towards the end of the lecture today. There are definite improvements. This is not by any means the best way to do things. I use videos. Again, that may not be the best technique, but I did that. The information there on what I did it with. The second part, the images, need 4 images. The images themselves are the P's in these equations. The subscripts indicate the angle. The angle is arbitrary. It's simply reference to one of them. In principle, I ought to know which way they were oriented on the sky too. For this, I didn't bother trying to track that. I just wanted to see whether you could see any results. Stokes parameters are one of the common ways of representing polarization. There are actually 4 of them, I, Q, U, and V. I don't need V. V is related to circular polarization, so I didn't even include that on here. But you can get it out of the 4 measurements. The results we want is degree of polarization, pi, capital Pi there, and the angle of the angle of polarization, the angle of maximum polarization, theta. You can get that through these calculations. You can do most of the calculations in any image processing program. For what I'm going to display later, what's going to be displayed is the intensity I, which is simply a combination of 2 of these images, which would be what you'd get without a polarization filter. The square of the degree of polarization, simply because I haven't taken the square root of an image yet, and the tangent of the angle polarization, tangent theta, where I'd really prefer theta, again, because I haven't implemented the calculation. They can be done. I just haven't gotten around to doing it yet. I'm going to show results on 3 particular areas of the moon, just to show what the effects are. These images there, Aristarchus region. The leftmost image is the intensity image. That's what you get with just white light. I didn't use any color filters with these, by the way. They're just white light. The degree of polarization squared is the upper right, and the tangent of the angle is the lower right. Now, tangent angle, you got to remember, goes from -1 to 1 as you go from minus 90 degrees to 90 degrees. So in order to display the tangent, you've got to bias it enough to get the -1 up above 0, because any negative numbers in an image will display as black. So they're biased up. Let's see here, the brightness in the pi squared image. Excuse me. In the pi squared image, the brightness is related to the degree of polarization. The brighter it is, the more polarization there is. I haven't made any attempts at interpreting this yet. As a first guess, and don't hold me to this, somebody may correct me on it. I did the darkest areas right there at Aristarchus. In the crater, I would assume that's a fairly rough, fine-grained area. That would give random scattering, which should give 0 polarization, I would think, net repolarization. The flatter areas have a little more polarization. The angle, there's really not much going on there. And some of the others you'll see a little bit more variation. Some in the extreme peaks, things right near the peaks of areas. Copernicus area gets a little more interesting. Copernicus, Kepler, then your normal image. Degree of polarization, again, you see the crater itself turns out very dark. The rays show up very nicely, the degree of polarization. And you see the other craters in the area showing up as dark spots. Angle, you do see more variation around here. Keep in mind, this is, it was a gibbous moon for these images. So you're looking more or less straight on it. Copernicus is a flat surface. Aristarchus was over close to the limb looking at an angle. So you have, in Aristarchus, you have a fairly biased, fairly large angle reflection overall. You do see a bunch of variation here. There do appear to be things to see. The other side of the moon, the Mare Crisium, the surface is tilted the other way with respect to us. Again, the degree of polarization, you see a fair amount of results here. Darker areas. The bright areas on the flat Maria correspond to the flat Maria. Again, the angle doesn't seem to show too much variation. There's fine scale variation here, but it's hard to see what's going on there. The main point there is that there does appear to be some results. Now, from this, there are a few things I've learned. Some of them I anticipated. As far as problems go with the technique, using multiple filters means you have to calibrate every filter individually. Like I said, you're looking at percent level differences in the intensity. The calibration has to be pretty good. Multiple filters, you're getting non-simultaneous images. Now they're only a few minutes apart, so in the case of the moon, it probably doesn't make a whole lot of difference. But it's not ideal. And you have to register the images from the individual filters. Other possible techniques. One I originally thought of and didn't have the equipment to do it properly. Let's use a single filter and rotate the filter. That for my equipment, that ended up, you had to remove the camera and remove the filter and actually rotate it and put it back. So there's a whole lot of problems with that. You could implement some kind of rotator. That would involve some mechanics. Or you could do like Tom Gerald tried one time for stellar astronomy and rotate the entire system. No, I think he tried to rotate he was rotating the entire telescope for stellar polarimetry. It would be possible to put a rotator on the focuser and rotate the filter and the camera simultaneously. That would change the angle of the polarizer on the moon image. You'd introduce some problems with having to rotate the images to be able to superimpose them. But it would probably work. Individual images in a CCD camera instead of a video would also probably be better in the sense that you'd have more control over the way the image was stored and then the camera processing. I don't think it'll make a whole lot of difference though. And it introduces more problems of trying to get multiple images to improve the resolution. Other types of polarizers are also possible. Most of them involve more equipment in the way. The simple linear polarizer filter is very easy because you can put it in a standard filter holder. And one of the things I didn't find out about till later, actually fairly recently, just a few months ago, There is such a thing as polarization cameras. They're CCD cameras. The principle is like a color camera where you use 4 different pixels for the colors with color filters on, but there are 4 polarizers built on the CCD or CMOS detector. Instead of a color bare matrix, you got a polarization matrix of 4 images, 4 polarizers. These are commercially available. There's actually several companies that make them. QHY is the only one that's designed for astronomy. They've got one designed for astronomy. I think maybe all of them use actually the same Sony chip. I think it may only be one company that makes a polarizer detector. I may be wrong on that. The QHY one is a little bit pricey. It's in the $3,000 range, and it's a special order. There are others that are designed for industrial things. They're used for industrial process control. The problems with those are they're not designed to mount on the telescope. They're not. Their output isn't usually USB. It's typically a more proprietary. It could be used. Thor Labs has one out that they actually provide the software for it, that they'll do all the analysis for you too and provide the polarization parameters. But the interface problems might be greater. I haven't really looked into that. There are possibilities. The polarization camera seems like it may be the way to go. You get all 4 images simultaneously. And there may even be a way to take color processing and modify it to produce the polarization parameters directly. At any rate, it wouldn't be any harder than the four individual filters. So in summary, I think I've demonstrated that lunar polarization is detectable with amateur equipment. Now, like I said, I wouldn't attempt to measure scientifically, quantitatively, what the results were on this. Qualitatively, I think I've demonstrated that. There are better techniques than the one I used here. And in fact, I'm thinking about trying the polarization camera technique. It appears that some software development is needed. I haven't been able to find any software that would meet the needs here. There is software in the Space Telescope Science Institute, FITS libraries that can be adapted. All the subroutines you need are there. Like I said, the polarization camera may be the best way to proceed, the easiest way. And some of the questions that we've investigated: does polarization vary with the lunar phase, time, or wavelength range? One of the simple possibilities would be to try color filters with this. It would also probably increase the polarization contrast, because the polarization efficiency of the polarizers varies with wavelength. So they tend to dilute things. Other objects, other solar system objects, are another possibility. Basically, the only problem with leaving out, I skipped over one thing. I said it's going to tell you what the effect was of not having the bias. Basically, it doesn't affect the calculations at all, except that it dilutes. It adds a bias in where you have to divide things. There's no bias. The bias gets canceled out when you subtract, but it doesn't when you add in those equations on the earlier slide. Let me go back to those and point out which one. Basically, on the Q and P, the S1 and S2, the bias subtracts out. We're just subtracting 2 images. The intensity, you've had the bias added into it. So the degree of polarization, you're actually diluting it. You're dividing by a bigger number than you should. It doesn't affect the angle at all. So that's what I have to say. Anybody have any questions? We're probably run out of time.
Yeah, Bailey, right, yeah, that was very interesting. I wondered if the polarization worked the same way with Mercury to study how the light reflected from Mercury, just like the same way the moon reflects back to us. I wonder
I
if
would
there's
really
anybody done
expect
that.
it to. I would really expect it to. The surface is basically a solid surface, similar to the moon. The
Right,
I mean,
yeah.
the problems there would be the size of Mercury. You'd be getting averages over very large areas for amateur type telescopes. That might tend to average things out, and you might not see any result. It'd be interesting to try.
Yeah, it proves to be very difficult. I mean, dealing with a small disk too close to the sun. It depends on the solar angle too. I mean, you see
Yeah.
the way reflected, albedo changes during the solar angles or something like that.
Right.
Okay, we're going to go ahead now and thank Wayne. That was a real tech talk. Thank you, Wayne. Perhaps a few people here will finally delve into polarimetry, lunar polarimetry, or in Frank's case, that's something else for his Christmas list.
Yeah.
Thank you. Thank you again, Wayne.
Well,
okay. Let's move along now to successor to the Lunar Topographical Section Program Coordinator, Lunar Section Coordinator, David Teskey. David lives in, now is it Louisville or Louisville, Mississippi?
Louisville.
Louisville. Up in the extremely populated, wait a minute, it says here, out in the middle of nowhere, northeastern Mississippi, with his wonderful wife, noisy Chihuahua, and 5 cats. Dave's originally from Duluth, Minnesota. He's retired from a career in science education, including at planetariums, environmental centers, and teaching in public schools. As such, he has received a number of local, state, and national awards in teaching. Oh, we need you. Boy, do we need you, David. He's been interested in astronomy all his life. The interest was likely inspired by the Apollo missions, now 55 years ago. It got him interested in all things astronomy, specifically lunar and planetary studies. He's been an active aLpo member since 1994, but since 2019, he's been the coordinator of the Lunar Topographical Studies section, MAPS, Surface. This has included editing and publishing the monthly newsletter, The Lunar Observer. He has great, is this a typo? He has great fun corresponding with fellow loonies across the globe. He enjoys all observing, especially solar and lunar. And his talk today will feature how the TLO has grown and how you can contribute to it. So I know we went over, but I want you to do a good job. Take it away, Dave.
We'll try. Hey, thank you. Let's see. Is that right? Can you see that?
Have you started the slide? There we go. There you go.
Yes, we did.
Okay, you can say. Oh, welcome aboard. I'm here to talk about the Lunar Observer newsletter.
It's not full screen though, David.
I'm going to try to. Okay. So how do I do that?
There it goes. You're set now.
It's going?
Yeah,
It's
you
full
look
screen,
you look
David.
good. You look good.
You're good. You're good.
Okay. Thank you. I'm going to try to get you to join and send more issues or articles and images to the Lunar Observer and look at one fun study of a lunar feature. As Ken mentioned, the Lunar Observer is a monthly newsletter of the Lunar Topographic Studies section of aLpo. It actually started in 1998. with William Dembowski up in Pennsylvania. And then in around 2008, Wayne Bailey took it over. And in 2019, I got it. And it's a fun thing to play with. And I'm going to look at specifically the last issue of the Lunar Observer for a while so you can see what's in it. For the July 2024 Lunar Observer, 116 observations of the moon were made. These were made by 34 contributors from 12 countries around the world. I started something a couple years back by the numbers so we could look at the countries and equipment used. And it shows that on the top graph where observers and observations per country are made. And almost always Argentina wins. The USA is often in second place, but Italy sometimes takes over. And if you look carefully at that graph, you can see that the Latin American countries really do send in a whole lot of observations, and that is in part thanks to Alberto Annunciato, who is our assistant coordinator, who does a great job rounding up people. I also keep track of the telescopes that are used for observing the moon, and up until last year, it was pretty much Maxitovs and Schmidt-Cassegrains that did the most of the observing, but lately it's pretty evenly split between classical and non-classical telescope designs. And most telescopes are small, between say about 50 millimeters to 8 or 11 inches. Sometimes we get a C14 in there, and every once in a while we get something bigger, but usually it's 5 to 8 inch telescopes. Here is an example of an article that was published in the July Lunar Observer by our very own Rick Hill. This past year, we had 105 articles published, which is about 9 articles per issue. And these articles range from one page, like this one of Rick's, to articles that range into 40 plus pages. So we get a wide variety of articles. Such as on this page, we see often sends in an article about wrinkle ridges. That's his area of expertise. And he often makes a drawing like you see here with his 4-inch Maxitov. And he also compares that drawing with photographs taken by other observers or even satellite images of the moon. Recently, on the right-hand side, we see Robert Reeves started contributing to the Lunar Observer. And as Bob Garfinkel said yesterday, he's a great lunar imager, well-known, so I'm glad he's sending in material. Other articles include, on the left-hand side, last month by Paul Walker. He's in Vermont, USA. He gives us an observing report, this time of Mare Frigoris. And on the right-hand side, we had a lot of compliments on this article about a quick study of the Grusium region south of Mons Delta. This was by a new contributor, John Smith in Nashville, Tennessee. And what I bring to your attention here is there's a black and white image from the Lunar Reconnaissance Orbiter of what he was studying. There's an insert from the Chinese Academy of Sciences map of the moon, which is of this region. And down below, there is an even more detailed map from a gentleman, John Robbins, who has made maps of the moon. So we get a lot of different sources there. The main part of most of our lunar observers is something called the Recent Topographic Studies. And this contains images, drawings, and short observing reports from our observers, such as here we see on this page from Gregory Shanos in Florida. He has a one-day-old crescent moon, which is an awfully good catch. We see from New Zealand, Maurice Collins, with his photograph of Rups Recta, the straight wall. Great image there. On this page, we see Poinsettias by Walter Ricardo Elias of Argentina. Again, Argentina is very well represented of Poinsettias. Maurice Collins, again in New Zealand, last month sent in a picture of Plato. But if you look very carefully at his image of Plato, there is a hook shadow on the floor of Plato, and that actually was the subject of 2 articles in the summer issue of the journal. So that's pretty cool that he captured that. On the right-hand side, Larry Todd took an image of Theophilus. Great image there. And we do get really nice drawings. Tarantius, which is just south of Mare Crisium, this was sent in by Istvan over in Budapest, Hungary. Beautiful drawings that he sends every month. And on our screen right now, or on our meeting, I hope, is Tony Cook. These 2 columns are contributed monthly by Tony Cook. Besides doing these 2 very fine, well-researched articles every month, Tony is the director of the British Astronomical Association's Lunar section and the editor of their lengthy newsletter, the Lunar Circular. I don't know where he has time to do all this, but he pulls it off. On the left-hand side, you see Lunar Geologic Change and Detection Program. So what he's doing here is he's looking for transient lunar phenomenon, or perhaps looking at data to say, did it happen in the past or not? He'll be given a talk about that later. And he also has a new section on buried or basin and buried craters, which looks for, just as the name implies, features that aren't too easy to see. Each month we have a calendar of what's happening on the moon. We try to get readers to join aLpo, and I think we've done pretty good on that. And very importantly, we have guidelines on submitting images to the Lunar Observer. It's pretty straightforward. It's the same guidelines that have been there for a long, long time. But I've had a rash lately of people who send in basically everything they have, and they're not very well documented, and they really need to be well documented scientifically. So here we see, for example, Copernicus, the date, the time, the observer. At least we can track it down that far. I also map out the various formations that our observers mapped. And July actually was the strangest month I've mapped so far. If you look very carefully at our map, there's 11 ends mapped. But the big ones like Copernicus and Tycho and Clavius, they weren't looked at last month very much. That was odd. There is a Focus On article in the July 2024 issue of the Lunar Observer, and these Focus On articles are a bi-monthly series that highlights a specific lunar feature or features. They are written by Alberto Annunziato down in Argentina, and these articles solicit images, drawings, articles, and written descriptions from observers around the world. In the last year,
what do you want to search for?
in the last year, our Focus On topics have included Mons Rumker, floor fractured craters, Dorsus Smirnov, Sinus Iridium, Lacus Mortis, and crater chains. Typically, these articles range 30, 40 pages, that in that ballpark, and goodness, maybe 60 images. I can't obviously show you all the images. I'm just going to show you a handful and where they're from and who they're from. A year ago, Mons Rumker which is a beautiful dome area in the northwestern quadrant of the moon. We see images by Felix Leon up in or down in the Dominican Republic, Massimino Dionisi in Italy, our very own Rick Hill, our lunar extraordinaire. In September, we looked at floor fractured craters, which had a tremendous amount of images came in, which was great. Howard Eskildson in Florida looked at Atlas and Hercules, and you can see using the Lunar Reconnaissance Orbiter, he looked at how their floors were shaped. Fabio Versa over in Italy, in Milan, he looked at Posidonius, and Jeff DeWitt in Belgium took a look at Posidonius as well. In November of last year, we looked at Dorsus Roberto Annunciato in Argentina. He sent a beautiful drawing he does each month. Sergio Bambino in Uruguay gives us very beautiful images, and as does Paul Walker in Vermont. At the beginning of this year in January, we looked at Sinus Iridium in Marcelo Mujica of Bolivia sent us that image. Larry Todd of New Zealand sent us a beautiful image. Carl Elias sends us images every month. That's a nice image of Sinus Iridium. And Francisco Elise Cardinelli, again of Argentina, sent us a nice image. In March, we looked at Lacus Mortis, the Lake of Death, up by Hercules and Atlas. And here we see a beautiful image from Desiree Goodney, a beautiful drawing from France with Marc Deconic, and some character named David Teskey also contributed an image. And the last focus on we'll look at right now was crater chains, and in particular, a beautiful crater chain called Crater Chain Davy or Cantina Davy. This is from a asteroid that must have broke up right before impact and left a line of craters. We see them from Cesar Fortuné of Argentina, Gregory Chavez in Florida, and Germain Saver of Argentina. We always like to keep our observers up to date on our future focus on topics. The next one coming up in August is Aristoteles and Eudexus. We're already getting quite a few images in of that. You can see it in the next year the topics have, so that our observers can go out and try to image, for example, Clavius. Get images ready for that. New this past year, this is my 5th year of looking at the Lunar Observer, is some observing equipment, especially the SeeStar 50, which is a smart telescope. Greg Shanos of Florida has used this telescope extensively for lunar imaging and wrote an interesting article using the telescope. After our break, I believe he is giving us a talk about the SeeStar telescope and what he's done with it. Is this the future of amateur astronomy? Guess we'll find out. I'm impressed with this slide right here. In the past year, we've had 69 observers from 19 countries contribute 1,180 observations of the moon in this past year. I don't know how that compares with other years, but I think it's a pretty good year. And if we look at our graph, again, we see Latin America is very well represented with the number of observers per country in the last year. But we have a lot of countries, China, Malaysia, Hungary that we have a handful of observers from as well. This is, I got this from Bing, but it gives you the impression. The total number of pages of the Lunar Observer this past year were 1,234, which averages 103 pages per month. And Ken knows this very well. We print out a couple of copies of this, and it's a lot of pages. This past year, we got the Lunar Observer put on the home page of Nights. And if you're ever look at Cloudy Nights, which is a great place with forums and stuff for sale and such, there we are right on the front page, the aLpo Lunar Observer. I've put the Lunar Observer on Cloudy Nights each month since 2020, and in that time it's gotten many views, contributors to the Lunar Observers, and even some aLpo members. But starting this past February, the Lunar Observer was put on Cloudy Nights homepage, and that drastically boosted its exposure and number of views. And the people who run Cloudy Nights also put the aLpo comment section on the homepage at that time as well. And I really believe that as many people as possible who are interested in these topics be exposed to them. At a board meeting last night, we talked about, if you look for some stuff like lunar observing, where does it come up in your search? And this is a little graph as of the beginning of this month. We can look at the number of views on Cloudy Nights the past year. And from last July to January, we had between 300 and 400 views a month, which I thought was pretty good. But in February, once we put it on the home screen, we jumped up to 1,700 views per month and then settled in the 800 to 900 range per month, which I think is fabulous. So you're saying, Dave, what do we do with this stuff? I want to contribute my lunar observations. Please submit your lunar articles. You can write articles, images, drawings, reports to me. And on the new website, you're also going to see other places you can send it to. Please remember that no observation is insignificant. At the end of each month, I send out lots of emails of the Lunar Observer to individuals. So let me know in the conference in the chat section if you want me to send you the Lunar Observer. But on the new aLpo website, once it's up and running, there will be a place to subscribe to the Lunar Observer where it will be sent to you automatically, and then we won't have to do all these individual emails. So that is the July issue of the Lunar Observer. I want to finish up by looking at a cool lunar feature here. Want to do a brief study of the craters Messier and Messier A. These are twin craters in the Sea of Fertility that are very interesting lunar craters. Messier itself is 9 by 11 kilometers in size, and Messier A is about 13 by 11 kilometers. Stretching from Messier A to the west, or in this case, the left, is a striking double ray, and it looks very much like the tail of a comet, with Messier A as the head of the comet. That makes sense in name. Of course, Charles Messier long ago was the great comet hunter. And here's some pictures getting a closer and closer view of Messier. You can see in the right-hand side that double ray to the west. Here we are getting closer and closer. Wow, that's cool. I'm not much of a very good at drawing things, but I have tried my hand at drawing objects like Messier. And when I do that, I look at a feature like this and I wonder what could have caused these craters with this double ray out of Messier A and the butterfly rays go to the north and south. What could have caused such to form? So I've been fascinated with this crater a long time.
Up until the
It
time,
was likely formed. Yeah.
up
Go ahead,
until
Rick.
up until the time of Reverend T.W. Webb, these two craters were thought to be identical. And he was the first one to show that they were anything but identical.
I saw reference they were two peas in a pod. I don't know.
Yes, that's right. That's what I think it was Beer and Modler called it.
Beer, yeah.
But
what-
David, it's possible it could be, one impact, then it bounces to another area, a second impact?
That's what they figured did it. The double crater was likely formed from a small asteroid striking the moon at a very shallow angle from the east, which is to the right here. And the asteroid formed Messier. It ricocheted and formed Messier A. And it spread the rays downrange. A few 2 or 3 years ago, I went to Huntsville, to Alabama, to the Space Center. They have a planetarium there, and I do a lot. In my past, I did a lot of planetarium stuff. So I went to the program there, and they had, for whatever reason, they chose Messier as their object on the moon. And they had like a fly-through of the crater. They went right into it. You could see boulders and all this stuff. It was just awesome. If you ever see it, take a look. Well, if you want to really take from your house another look at a crater like, say, Messier, you could look at images from the Lunar Reconnaissance Orbiter to investigate these craters or anything else you want on the moon in great detail. And these are, again, our images from the Lunar Reconnaissance Orbiter. We're getting closer and closer. Look at the scale on the bottom right. And getting closer and closer. Remember, that's 10, 12 kilometers across. You can, even with the Lunar Reconnaissance Orbiter at home, map out the craters. Here I drew a line across the middle of both craters. And on the right, you can see where the craters, how they're shaped, how their profile is. So you can learn a lot about them. And if you think about it, nobody else has drawn that exact profile before. So who knows what you can learn when you do this. You don't even need a telescope to do that. So I invite you, please join us on this journey of lunar exploration. You can use images from the Lunar Reconnaissance Orbiter. That's just one way, one of many ways you can study the moon. I invite you to share your lunar observations with the Lunar Topographic Studies section. It's not the only lunar section we have. Tony Cook will be talking about lunar transient change. Ralph Lena, he's in charge of domes, which is a tricky area to study because they're so subtle. And Brian Kudnick is in charge of lunar flashes, basically meteors striking the moon. Thank you for your attention. Open it up to any questions here.
Let's keep the questions one question because we're running late. So who has a question?
Well, I just a statement that this is Bob Garfinkel. Messier A was originally named for Pickering and was later changed to
Pickering, that's
Messier
right.
A.
And he was a real oddball.
Yep.
Real oddball. Okay, let me thank David. But with all of you
Thank
here,
you.
I want to make a statement. I got an email last night from Thomas Giguere, and it applies to possibly several of you that have our section coordinators. He says, I would like to identify contributions to the aLpo from the late Michael J. Morrow of Ewa Beach, Hawaii. Now, this would have been in the 60s into the 80s. He passed away a week ago, and he had mentioned that he had contributed drawings to the aLpo but we don't know exactly where they are. So he's asking for some assistance on this. Now, I wrote back to ask where this was, who he sent them to and so forth. And the answer I got was he doesn't, the writer of the email to me doesn't really know, except that when he first met the gentleman in the mid-90s, he thought he mentioned Jupiter observing. So that would probably put it back into the 80s. He was a board member of the American Meteor Society, and he worked with Dr. Charles Olivier, Dave Meisels, and later Bob Lunsford. But he doesn't recall him reporting to the meteor section of the aLpo. So again, if any of you have any knowledge or ideas as to any illustrations or images submitted by the late Michael J. Morrow, Morrow, please contact me. And I'm at poshedley@bellsouth.net for the time being. Okay, we're going to move right along now to our next presenter, Mr. Frank Melillo. Most of you were here, probably all of you were here yesterday, so I'm going to scroll right through the little intro I have on Frank. He is our Mercury section coordinator, lives with his family in Holtzville on Long Island, New York, while he's in the insurance industry, and that's unrelated to his aLpo duties. We find him indispensable as our go-to person regarding this oft-ignored planet.
Jane, I'm talking right now. Okay. Right.
Okay. And we can always count on Frank to provide even the most minute details as to when and where Mercury can be observed, as well as any features that might be seen. Now, the topic for this talk, I don't know if it really relates to Mercury, is called Catching the Nearest Star. So we're a little bit behind. So Frank, see what the best is you can do. And then we're going to go on break. Okay. We'll go on break right after you're complete.
Okay. Yeah. All right. Thank you. Thank you, Ken. Okay, I'm going to share my screen. Yeah. So those of you who were there yet today, and remember my talk about what's up with Mercury 2024.
Frank, click on from beginning at the top left of your screen under the file menu. A little more over. No. Yeah. No. I guess.
Got it?
Let's see if it works. Okay.
Okay. Did everybody see the screen?
Yep.
Okay, great. All right. Not only observe Mercury and the planet, but I do observe the sun also. Now I have more time to do solar research, basic solar research and solar terrestrial studies and all. And thinking that I would be retiring, I'd spend more time to do more solar observing. This is okay. I've been an aLpo member for the last 40 years, and also observed the sun for the last 40 years too. And I usually contribute to the solar session, which is run by Rick Hale, our own Rick Hale. He's the coordinator, and he still is after 40 years. And I believe the solar session was found in 1982, if I'm not mistakenly. And so it's over 40 years, and it's really, really active session, and I usually contribute to the solar session on and off all these years. But lately, for the last few years, I've been now doing a lot of solar observing. I find the solar observing very, very interesting because the sun is always changing. And I'm being concentrated in doing this now, in addition to planetary observing. So the title of the talk is Catching the Nearest Star. Okay, you probably assume that I'm going to talk about Alpha Centauri. No, of course, the nearest star to our sun, yes, it's Alpha Centauri, but I'm talking about our own sun, which is the Mason star. Now, our sun, our star, is the only star in the universe that we can study up close. So I'm going to show you some of the basis research that I'm doing to the solar session. What are the advantages and disadvantages of observing the sun? Okay, well, let's we'll break down. These are the advantages. We all know that the observation can be done in daylight. We don't see the sun at night, right? And you don't lose any sleep. That's one of your major advantages of doing the solar observing during the day. There's plenty of light. You don't have to worry about, if the sun is too dim or something like that. And you can observe the sun in the backyard. It's not like you have to go someplace else where you can see the sun. You can own from your own property, your own backyard, and no need to escape light pollution. So you can observe the sun right in the middle of Midtown Manhattan, Times Square, and you do a solar observing. And I did it once with my daughter a while ago. You don't need a monster telescope, and a small refractor would be just fine. And like a small telescope is just fine, a reflector or any refractor would be just fine. The sun is constantly changing. So the sun never looked the same as the day before. It always changing. And the sun looks the same never looked the same as the day before. So it's always constantly changing. That's what it is. You look for the change, and that's what makes it interesting. And it's always something new to observe the sun. Okay, all right, there's some disadvantages. The sun causes blindness if you're not careful. We all know that. Observe the sun very, very carefully. Make sure that the filters that you're using for the telescope, make sure that it's secure on the telescope. Make sure that it's tight and all, and just make sure, if you have people around you, make sure the filters secure tightly. You will run into atmospheric turbulence, disturbance. So, at the sun heating the atmosphere, then you get some kind of wave, and then you get some kind of turbulence as the sun rises into the sky. The clouds may build up during the day because of the heat. The wind may pick up because of the heat. The narrowband filter may be quite expensive. So if you talk about the calcium light, you talk about the aLpo light, it may be quite expensive. Okay, you know that the cycle 25 now is currently we on the cycle 25, and it's approaching to the maximum activity, hopefully within a year or sometime next year, 2025. It's just to give you an idea that during the solar maximum, which we're approaching right now, you see a lot of sunspots starting in 30 latitude north or south. It start to migrate toward the equator. And during the total solar minimum, and you can see very few spots, and then we have spots along the equatorial region. So it's like, it start from the higher latitude during the new cycle and gradually get down to equatorial level, and during the solar minimum, then it started again at the new cycle. The next one, to give you an idea, is that the cycle 25 is pretty active as of now, because it had a very high, steep number of sunspots approaching to the maximum level. So hopefully sometime next year, 2025, it would be the maximum. So so far it looks good. As you can see, there's a lot of up and down because it's 1 month you can have a lot of sunspot. Then the following month you get very few sunspots. So there's always up and down, but on the average, it is rising very slowly to the maximum activity. It's possible, hopefully by next year. Okay, this is my telescope setup. You can see that. With the Selection 8-inch telescope, that's all you need. You don't need a monster telescope. And over here, you see I'm doing it with the binary view, and viewing 2 eyes better than 1. But you got a clearer contrast, clearer picture of the sun. And you can see with the aLpo filter, which I'm been doing a lot of work on that. And of course, I put the shade here, the cardboard, to make the shade here, so nothing will go to your eye when you look through the eyepiece. So this is basically on my setup. Okay, now these are the basic solar research that the amateur can do, not only for myself, but other people as well. You know, there are very few professional solar astronomers there, but you know, they working on the satellites, they're working at the observatories, you know, institutions and all, and they leave very little solar basic work left for the amateur astronomer, and that in order to fill in the gap. So I'm going to show you some of the examples that the amateur can do, which make it very interesting. So, like for example, the granulation. Right, this is what taken in white light. You see a very narrow, high resolution sunspot. Yeah, and you can see the study the granulation. That's one of the nicest way to do it in white light, to study how the granulation works by convection. And if you look at the next one, it's a little close up. It's not a very good picture, but as you can see some cells here that they're coming in and out during the convection. You know, it's like very similar to when you see a boiling water, and you see a lot of bubbling go to the top of the water level, and you see the bubbling pops out and all, bursts out. So it's the same thing, like in very slow motion, the same thing you see on the sun. So here's probably a better picture. You know, a single sunspot here. You can see all the granulation. It's very, you know, doing a very excellent, nearly excellent scene. You see like a fine grain here, and here's the close up. You can able to see individual cell. Some of the round, some in poly shape, polygon, and you can see the interlane here. It's divided up the cells come and go. Here's another close up here. This is probably the best shot of the granulation I have here. You can see the lanes clearly here, and you can see the shape here, all different shape. Some are round, and you know, they have irregular shape, polygon shape, and they're popping in and out. It's very hard to see like in still picture, but what I did was the other year I did 9 images and converted into a short animation, and you can see the change of the granulation here. Here's one example of the sunspot. You can see the change in there. It's hard to see if you keep your eye on one area, and you can see the change of the granulation, especially around the sunspot. It seems like it's moving away here, and you can see some fiber of the penumbra here. You can see it's moving out. So it's like it's moving away from the sunspot. So this is contain 9 images within 24 minutes, 1511 and 1530, about 20 minutes. So that's just one of the examples that you can do in white light to study the granulation. You know. Okay, another one, the Wilson effects. This was seen by Alexander Wilson back in 1700s. He was the first one to recognize that the sunspot seems to be elongated. Here's a close-up shot if you want to see here. You can see what I mean. You can see the sunspot, especially along close to the limb. You can see like it's like a sausage shape, and you can see the depth of the umbra. You can see the depth there, and surrounded by the penumbra, and you can see that it's the umbra, the spot itself is below. It's below than the surrounding area. And here, when it's the center of the sun, you can see it's more circular here compared with the edge of the sun. Over here, I make the light intensity, and this is the same as this image here. You can see the intensity. You can see the umbra is much larger here, and the umbra on this side is closer to us. It's shorter. So this is, you can see the profile much clearer. You see the umbra here, and much wider here, represent this here. Then here, this image here, you can see that it's evenly spaced out. So, so this is one way to look at it, to study intensity here. And this one here, you can able to see along the edge. You can see that it's like they have the depth of field, the umbra, and surrounded by a penumbra. And this is
programmed.
yeah.
Excuse
Yeah.
me, what program did you use to make those graphs, Frank?
What software I use?
Yeah.
This is WinJupyter. WinJupyter.
Oh, WinJupyter. Oh, okay.
Yes, yeah, they have a line intensity. You can study the brightening, photometry brightening, and line intensity. So yeah, you can see the profile of lines that you can able to analyze, how it look from certain angle, Yeah, so and also the filament. Yeah. Let me put this in here. Okay, the filament eruption. What I did here, if you look closely here, this is the raw image of one filament that I took here on the blue wings. And this is the raw image. I did not process this, no processing at all. This is just straight from the raw image. And you can see the filament here much darker in the blue wing of the H alpha line. But on the red wing, it seems like it disappeared, or maybe it's just fading here. So what telling me is that it's a possibility it could be eruption, or it's moving toward us. The more they move toward us, the darker the filament will be. And this one here from the National Solar Observatory, GONG, and you can see this is the same filament that I took in my image here. And this was taken just shortly after I took the imaging. And you can see, I don't know if how well you can see the time, but this is about an hour later. And you can see it start to erupt it. This is about 10 minutes later. Another 10 minutes later, you can see the eruption and so forth. So it's always good when you have a filament like that. It's always good to check the blue wing of the center line of the H alpha center line and the red wing, and you can see if there is any motion involved. And sure enough, I predicted that someday, some short time later, it's going to be erupted because in the blue light it seems like it's moving toward us. And sure enough, there was a filament eruption there. So that's one of the things you can analyze, if there is a nice sized filament on a disk. Okay, the filament and the prominent connection. You can see here a very large filament on the disk with the sun, and you can see that's approaching toward the limb. And then you have, okay, then the close-up, you can see when it's going on the limb. So, always to see the filaments on the disk, and those are prominent on the disk. Same way you see on the side on the limb here, because the reason the prominence look so dark here because it's absorbed the light and it emits cooler temperature. When it's a cooler temperature, it emits less light, and so that's why it appears dark during the absorption of the cool gas. So when it reaches to the lamp, like you see here, it turned into the prominence. So, and it's just one image here back to the disk here. So, and hit another one, same thing on the disk on the lamp here, and then as it's rotating into the disk, it becomes like a filament. What you see here is the same thing here after a few days later. So that's not a way to study the connection between the filament and the prominent, how to look like when it's on the disk and how to look like when it's on the edge here. Here's our prominence. Eruptive prominence. When there is a flare along the side of the sun, and you can see all these rays here that shoot up in the sky like that. You can see in real time if you stare closely at the eyepiece. If you sit staring at it, you can see the slow motion. It's just spread out like that. And because there was a flare here, I forgot what region number it was. There was a flare erupted there, and then I just caught it at the same time. And same thing was here. I forgot what group it is. There was a flare here, and then it shoot up nicely, like a spray prominence. It moved in real time. You actually see it move, and they just come and go. They come down and rain. So that's a nice way to one of the nicest way to study the eruptive parameter. You see about the magnetic field. It's controlled by magnetic field, and you can see how the flow, the parameters, as you go around and come down and fall back to the surface of the sun, and controlled by magnetic field. Same the loop parameters. This is very interesting. They were taken out just a month ago, and you can see here there was a flare along the, I think it's beyond the limb, and all of a sudden it just something shoot up, and you can see it form like a loop parameter overlapping one another. If I can able to count, I think I count like 4. There's one here, there's the second one, there's the third one, and here's the fourth one here. So one top of another like that. It's very impressive. Very rarely. I always look for, I always look forward to see the loop parameters, but this is nice size there. Yeah, and of course, there's a lot of people, posted on spaceweather.com, and then you can see, in slow motion. One of the guy put animation there. You can see how to form there. But you need more time to take images after images, minute after minute, to see the differences and make it to the short animation. So you need time for that. So that's pretty cool. I was stunned about this. Yeah. Okay, light bridges. That's very interesting. This is done with white light. If you look closely here, you can see the white light developing across the sunspot, the umbra. I don't know whether or not it's split up, if the umbra is split up, or there's a light bridge or quarter umbra. But this was taken one day. But look what happened the next day. It changed it. Now you have a slice across the umbra. Look at the difference in one day here. We don't understand how the light bridges form. Even the professionals, it's not very well understood. You're not sure how they form. They form on one side of the spot or form on this side of the spot, or they meet together like this over the umbra. We don't know if it's breaking up. You can see some granulation. If it's breaking up, then you see some granulation along the streak here. So this is one of the major things that the amateur can do to study the light bridges. And here's another example. It's the purple one right here. It's a close-up here. You can see it nicely around here. How this form, I don't know. It's very interesting to find out, but you have to follow up with something like this here. Now, if you look carefully here, you can see some brightness along outside the ring of the penumbra. Yeah, this is caused probably by magnetic field, and it caused some kind of irregular granulation, and seems to be smaller and controlled by the magnetic field, and that's why it seems like it's less or fewer granulation around the penumbra, but you can able to see the brightness changes as time progresses, and you can see outer part of the ring. So that's one of the ways you can analyze how the granulation affect the magnetic field effect around the sunspot itself. So, and this is all white light. So this, if you have a white light, and you can able to do this. It's very interesting. This is professional astronomer. They don't concentrate too much about these things. So. All right, the wave. I don't know why I should post it, but this is very interesting here. If you look carefully here, there's some kind of arc here, but I'm not sure if this is break away from the umbra or it's moving out. And same thing here. It's a close up. You can see here, but I'm not very sure if this is the wave that broken up or breaking out from the penumbra or from the umbra. So this is done with white light, but there are waves you can see in the H-alpha filter called the alpha wave and a Moreton wave. When if there's some kind of flare and they have some kind of wave moving away, that's very, very hard to observe. You need, I don't know what, if you on the center line of the H-alpha, or you have to be on the blue wing or red wing, I don't know. But this is white light, so I'm not very sure. I didn't follow up. I didn't know anything about it until after the process whether or not it fan out. So it's something to look at it on a high resolution to see whether or not you see something like this. The spike along the edge of the sun, And you can see a lot of like a burning prairie here. And you can see that the spike is coming in and out like this. But this is a still picture. This is one way to see how the spike will form, how they change in over time. This is through with the H-alpha filter. And so with the H-alpha filter, this is one of the nicest way to study the spicule along the edge there. You see how you keep an eye on it and see how they form. This is another example of the spicule. Look how big it is. If near any active region along the side, along the edge here, you can see this spike here. There's some kind of a surge prominence from the flare here, and you can see all this spicules are very thick along the active region, but away from the active region, the spicule is very, very small. Photospheric factor. You see in white light, you see some of the vein light around the sunspot, especially along the edge of the sun, white on the edge of the sun, because it increased the contrast because of the limb darkening. And you can see all the shape, veinlet shape, that come all the kind of shape. And what caused it by this? Well, because it emitted higher temperature and emit more light. Always active around the sunspot group, but never in the center, because in the center you look in the deeper part of the photosphere, but along the edge you look at the upper part of the photosphere and increase the contrast, and because of limb darkening, you can able to see the factor around the sunlight, sunspots. But that's a great way to study this, because sometimes you see the factor first before the sunspot develop, and even if it dies out, the remain of the factor remains there, and you can see it can last for months and months. And so there's one way to study the activity around the sunspot. And of course, there's another section here. You can see the brightness of the factor there. They're always around the edge of the sun. Okay, let's give you an idea. It's the evolution of one of the sunspot group 135, region 136.15, and you can see here how to develop in white light and so forth, and when it caught in the disk and all. And also, there's another group here. This is quite interesting. You can see here how to develop between white light and H-alpha light when it caught in the sun. And of course, this one here. Oops. Yeah, this one. Yeah, this one here. Now, the next one is very interesting. Oh, wait a minute. Okay, this one. This one is very interesting. This is one of the largest group that we've seen last May on the disk. There's also Quartz Aurora. And you can see a very interesting sunspot group. Look at all this here. And this is white light, and this is H-alpha light. You can see all the minor flares there are popping in and out and so forth. So that's the nicest way to study the evolution as it's moving across the sun. Okay, this is one way to find out if there is any flare on the sun. This is by solarmonitor.com. And you can able to determine what region you see the flare here, and the time, and what kind of flare it is, and number of sunspots in that group there. And this is the region number, and so forth. And you can follow up what region you look at it and see if any flare is being detected at that particular region. Of course, 136.4 was similar to the size of the Carrington event in 1859. My images, and they could compare with Richard Carrington, the British astronomer detected in 1859, and what he drew, something like this, is very similar to 136.64 region number. And this is a comparison. It's very similar to what he's seen back in 1859 compared to what we saw last May. And of course, it's Quartz of the Aurora So if you look at the next images, it's caused by aurora. This is the first time I saw it from home, and this is I was kind of stunned to see this. And so this is one of the ways that the amateur can study the solar terrestrial studies to see how the solar activity affect the Earth. And one of the purposes is the aurora. Okay, one of the biggest flare in my 40 years observing the sun is back in March 1989. This is one of the major solar flares that causes major blackout in Quebec. And you can see here, it's just like an explosion. And then like after that, you can see all the elements of rays shooting out from where the flare occurred. So even the last 35 years ago, I haven't witnessed any flare like this so far. So hopefully I will see one like this coming up during the maximum solar activity, the upcoming activity. So hopefully you guys can see something like this. This is absolutely phenomenal. Back in 1989. Okay, toward the end, if you ever have a chance to go visit a solar observatory, please do, because I don't know if some of you may or may not been in some of the solar observatory around the country. I'll give you some of the examples quickly here. This is Messier Solar Telescope's Cape Peak Observatory in Arizona. And you can see the diagram here, what it's like, how they observe the sun from up here, from mirrored up here, and go down to the underground here, and they have a little, like a facility down there. And I would try to go in there, and by the front door here, you see the plaque here, but they don't allow no visitor because it's very strict to the public. So I just stay by the front door. However, on the other side of the observatory, there's the door here where you can go in, and all you see like a hallway, like coming down from the top all the way down to the bottom. And I don't know how well you can see here, but there's the mirror up there. I don't know if they observed the sun at that moment, but the mirror up there reflects all the way down here. This is one of the ways you can check out Messier Solar Observatory. Mount Wilson Observatory, they had a 150-foot solar telescope, and took a tour there, and you can able to go in through the door. Here's the tour guide. Once you go in through the door, you're able to see. It's not a very big room. It's a little cramped there. So they project the image on the sun on the white cardboard to demonstrate how they study the sun. They don't look to the sun like to the eyepiece like we do, but they project it on the whiteboard, and they can study from there. Of course, it's so bright that you need a pair of sunglasses to look at it clearly. And also to demonstrate here the solar disk, and what you see like a little ball here, that's equivalent to the side of Jupiter to the respect to the size of the sun. So it just tells the people to realize how big is the sun compared to Jupiter, which Jupiter is the biggest planet in the solar system. And finally, I'll be in Southern California in early September, and hopefully go see the Big Bear Solar Observatory, which they have a tour every Thursday afternoon. So I've been in that area, and I signed up for it. So hopefully I'm able to visit the observatory. So please do, if you ever travel to the observatory, a solar observatory, please do, because it's very, very, very interesting to see there. Okay, now San Diego Observatory, thanks to observations to the coordinator, which is Richard Hill, which is right here, and also have Pamela Chabak and Kim Hay, also as assistant coordinators. So please do and contribute to the solar session, and especially during the upcoming maximum cycle 25 solar activity coming up.
Thank you very much. Thank you. Hey, Tim.
Yes, I think I saw her name.
Yes, okay, Tim.
Yeah.
Before we get into anything further here, because we are running late and we're on break now, how about we leave the audio on and let anybody who wants to talk to Frank, they got 15 minutes to talk or they can do whatever they do on break-in, and we'll reconvene at 3:15 Eastern time. How's that sound?
Yeah, start up when we're supposed to start up again. Yeah.
Yep. So everybody who is on session will unmute you, and you can talk to Frank until 3:15.
Sounds good.
Okay.
Yeah.
All right. Anybody have further questions?
Hello, Frank.
Yes.
I'm Jay Miller. I was just
yes.
couple of comments. One, the most beautiful solar pictures I've seen are the ones by Christian Valadrich from France.
Right. Oh, yes. Yes.
His are absolutely phenomenal. His are, professional quality.
Yeah, exactly.
And the other comment that I was going to make is that on Fridays, I live in what we call the DMV, the District, Maryland, Virginia, and I volunteer at the Air and Space Museum on Fridays. If it's clear, we're across the street at the Eisenhower Memorial with solar telescopes, including a real Dobsonian, solar Dobsonian, actually built by John Dobson. If it's cloudy, we're inside, and we have a large screen with images from the Solar Dynamics Observatory, and it's got a video there, a 10-second, 2-day video of solar activity. And I always try to talk people into buying a telescope, getting a solar filter, and I tell them about doing observing.
Yeah.
So I always try to get
That's
people.
great. Yeah, especially the public outreach. It always takes place during the day, and it's always something to see, and the people are amazing.
Yes.
By if you have a white filter, and show the sunspot. If you have an A-sharp filter, just show the
We have
prominence
both,
and all.
yes.
But I have to say, the European observer is much advanced. Their equipment that they have incredible images. Majority of the European people, they're just absolutely phenomenal. How they do the solar work. I mean,
Christian's equipment is absolutely fantastic.
Yeah. We exchanged an email, and I tell her how great his book was.
I have it.
Yeah, and book there, and some of the incredible images. You can't even tell the difference between a professional or amateur, especially the granulation. I mean, now you can see very clearly. It wasn't even done by amateur before. It's just a little that 20, 30 years ago, and it's not such thing seeing like that. But now you can possibly do everything. It's amazing. It really is. I'm stunned myself. How much the amateur can do. The funny thing about it is a very little. Especially the professional astronomer. They usually study the stellar astrophysics, cosmology, and all, and there are very few professional solar astronomers. I mean, they don't just walk in a solar observatory and observe what they have to do. No, they have to write a proposal. They have to, have to get approved. They have to go through the committees. They have to go through the budget problem, and hopefully the weather's good. And if you have to do any solar observation, if they're looking for a specific structure on the sun.
Yeah.
So they know the amateur sun are free to do anything.
All right.
Yeah.
Periodic. Hello, Frank.
Yeah, Richard.
Remember to unmute yourself if you're going to talk to Frank.
Okay.
Hello, Frank. I live
Yes,
on
David.
Point from 1966 to 82.
I'm sorry, with that?
You're
I
muted.
lived in Rocky Point.
Oh,
I
Rocky
lived in
Point.
Rocky Point from 1976 to 82.
Oh, all right. Yes, the Rocky Point. That's north of me on the north side of Long Island. Yes. Where are you
Between
now?
Port Jefferson and Riverhead.
Oh,
I'm in
okay.
Baton Rouge.
Oh, okay. Yeah, John Nagler, right? Um,
Yes.
yeah, yeah.
Yes.
I think you told me why you're from Long Island. Yes, yes. Port Jefferson
Actually,
is north of me.
I was born in. Right. I was born in Houston, Texas, my hometown.
Okay. How long ago you were
But
living
I
on Long
enjoyed the
Island?
whole time I lived. I lived there from 76 to 82.
Okay.
I
Yeah.
enjoyed it quite a bit. The first year I was on Long Island, they told me it was the first they had had years.
Yeah, yeah. I'm on Long Island all my life, so look, I never get away from here.
Right. Anyway, I just want to say hi and let you know I'd lived there for a while.
Yeah, I think I remember you told me that. Yeah, you live in Baton Rouge, Louisiana, right?
Correct.
Yeah, okay.
I think I told you that a couple of years ago at one of the meetings, I think, at one of the conferences.
Oh, was it the outcome? In 2009?
The only outcome I went to was last year. My group, we held it here. We were the host for it. And that's why I wasn't at the conference last year, the aLpo conference, because it was held the exact same weekend as Alcon.
Right. Oh, yes, yes. Oh, okay. Well, we have the outcome here in New York in 2009. Yeah. I ran the meeting for the aLpo meeting.
Right. Oh, anyway, as I say, I just want to say hello, see how you doing.
Okay. Yeah, okay, I'm still here. Still here, yeah.
Same here.
Hey, Frank.
Yes,
This is
Ken.
Wayne Bailey. Just wanted to let you know, I don't know how it relates to what you were saying in the aLpo, but back in the 60s, when I was in grad school, I worked on the solar telescope at Kitt Peak for a summer, doing observing there. And at the time, we did see, we're looking primarily in calcium K on the spectroheliograph. You could see what, if I remember right, it was about a 5-minute oscillation in waves traveling across the supergranulation.
Right, yes.
In calcium K, you see a network sort of like the faculae, but more or less over the entire sun, except right in the sunspots.
Right, yeah.
Bigger than sunspots, around the size of moderate-sized sunspot groups. And in
Yeah.
calcium K, you could see waves sloshing across the supergranulation and reflecting from the walls.
Right, yeah. The only thing that I didn't spend enough time about study the granulation, because you have to spend there numbers of minutes and much more time because there's a change there. But you take a still shot, then another still shot, then you take then you made into the short animation. You see the differences there, but you got to spend there more time to see how. If it's a seeing it's good, you can see the individual cells, how they form, how they die, how they form. So that would be very interesting, but you need time for that. And,
Yeah, well, this was about a 5 to 10 minute period. We only had typically about 20 minutes of good observing time in the morning.
Yeah, exactly.
And in one run, you can get half a dozen spectroheliograms, and we'd make a movie out of them. And you could see the waves sloshing back and forth across the supergranulation. And I don't know what the current status is. That maybe somebody else does at Kitt Peak. It had been closed for quite a time after the fire. I haven't been up there in a couple of years. They are open to tours now, but you have to make, as I understand it, you have to make reservations. I'm not sure whether you can actually get into the solar telescope anymore now. It was
Yeah.
retired some years ago. It's not an active scientific instrument anymore.
Which one is that? I remember which I heard
To
of
make,
something.
to make math, solar telescope.
Oh, okay, yeah. Oh, all right. Yeah, that's why. I think they changed the name. Did they change the name? I'm not
Uh,
really sure.
they, I think they had a
Uh,
Pierce to it. Either they call it Pierce Solar Telescope, Pierce
yeah,
McMath.
yeah,
They named it after Pierce, who was a division director at Kitt Peak for a long time.
right, yeah.
Mhm. But scientifically, it's been retired now. A couple of years ago, they were talking about opening it for tours and putting it back into operation for tours.
Right, yeah,
A
yeah.
couple of years ago, you could get into the observing room, but you didn't see anything in there except to tour the observing room.
Yeah, I thought yeah, they
weren't
closed it.
operating.
They closed the tour because of the pandemic. Now they open
Yeah.
up for it. Yeah,
Yeah, and there was just about the time they were going to open up again after the pandemic, they had the fire in Kitt Peak, and that closed them down again for a while. And I understand it's much more restrictive visiting now.
yeah. Like I mentioned before, I'll be in Southern California in early September, and I did sign up for the Big Bear Solar Observatory tour, which is they have every Thursday between 2 and 3 o'clock in the afternoon. So hopefully, I'm able to just take a tour there, so see what happens.
Well, Frank, I'd just like to say thanks for your presentation. I really enjoyed
Yeah, Howard,
what you showed. And I enjoyed the way you put together the development of these spots and their progression and their evolution. That was really neat.
Yes, yes.
One other comment I would make is, we're talking about some of these great telescopes that people have to look and stuff, but still, with a 3-inch telescope, you can get a lot of good detail on the sun. So a person doesn't have to be discouraged if you can't afford a larger telescope. I mean, and the nice thing about the smaller equipment is I've got a 3-inch or an 80 millimeter dedicated CAK. I've got a 80 millimeter Lunt H alpha, and then I've got a 70 millimeter white light telescope that was made by Orion for the eclipse, and it's got the filter bolted in front, so none of those can come off. I don't have to worry about that. I did have to laugh.
I know that's built in. Yes. Yeah.
I did have to laugh because I talked to Orion about that because they made that just for the observation of the eclipse. They said, but it's not for imaging. It does have kind of a cheap plastic focuser, but it works. And I think you've seen my images. The white light image is pretty decent even with that thing, but I never have to worry about is it got the filter on or not. Anyway, thanks so much, Frank. Appreciate it.
Yeah, thank you. Thank you. Your images are phenomenal. The only thing I didn't mention about I've been doing a lot of close-up. You don't see, it's very hard for me to get the whole sun. You need I have a longer focus. You need a shorter focus length telescope, or you need a larger chip for that. But I've been doing a lot of close-up and high resolution, and so,
Frank.
that's why you've been seeing.
Frank, to get the whole sun, get a SeeStar. I'll talk about that.
Yeah, you do. Otherwise, you do the mosaic. You take one shot
Yeah,
here,
yeah.
another shot there, then
Yeah.
you put it together. But that's a lot of work, though. But I've done that. If there is a large section of sunspot, then I can do like 2, 3 images all around and put it together, and that I can do. But for the whole sun, it's just too much.
Yeah.
The whole sun, what I did is I bought a 0.5x focal reducer, and then that made things really small. So did a little fiddling around, figured out how much, and I had a person machine off part of the nose piece, so it has an equivalent of about 0.72 focal reduction. That gives me a full screen without having to go through, combining images.
Yeah.
It doesn't have
great.
a good resolution, but it works.
Yeah. I have a telecompressor which converted to F5, but it helps. It widens up the field a little bit. It helps. Not much, but it helps.
Frank, this is Richard.
Yes, Rich.
I'm very interested in, you showed a line profile using WinJupos. And I want to learn how to do that because if you have unprocessed images, now you can stack them, but don't do the contrast enhancement, that sort of thing. You can actually get photometric data of individual, planetary features or sunspots, take your pick. And you actually sort of demonstrated that in your talk.
Oh,
You
yes,
showed
yes.
density going to near zero at the umbra, which is what you'd expect.
Right, yeah. Yeah, there is any like when I show you about the Wilson effect. You can see that, I was showing about the penumbra force when it's further away and closer to us, you can see from the angle.
Yeah.
You can see that, you can analyze the line. So you can do it would be done with the processing, but to do in raw images without introducing any effect to it.
Yeah, stack 100 raw images. I don't know, and even Gregory, you've contacted me from time to time saying, what can I do? And I might have you do some Jupiter images for me. Put them together. Just don't stretch the contrast. That's the big
Right. They got to be done in raw images.
Yeah.
Exactly. Yeah.
And then I want to take a profile north to south and get an intensity of, let's say, the north equatorial belt, the equatorial zone, south equatorial belt, and see if there's changes over time. That's what I want to see.
Oh, okay.
I don't know, Greg, is that something you think you could do?
Me, I don't know how to do it.
You just take images and then maybe add them together. That's all I want is the images.
Oh,
Yeah.
okay.
All right. Okay, I try that. No, not only Jupiter, but even Saturn too. Now with the ring edge, you can see both northern and southern hemisphere.
Yes.
And you can take. I try that. Yes, that's an idea.
Of course, Mars too, and yeah. So yeah, I would like to try that, Frank, and
Okay.
see
I'll
what
keep that in mind.
Yeah.
Right. I'd like to get started with the second half of today. Before Ken takes over and introduces our next guest, I again want to thank our sponsors for this conference, Celestron, Cat's Eye, and Explore Scientific. Like I mentioned earlier, we have some really nice door prizes. And remind you again that if you want to win a door prize, I've received about 22 emails, so that's perfect. But to be eligible, you must live in the continental United States, and you must register for the door prize. And the way you do that, you send me an email at cometman@cometman.net with the words door prize in the subject line. And if you can, add your name and address to the body of the email. That would be a lot better too. That way we don't have to hunt you down later if you win. Okay. After this meeting today, we will take a short break and then come back for the keynote address and the awards at 4:00 Pacific, 7:00 Eastern, and there's a separate Zoom link for that. So I will send that out soon after this meeting ends. Okay, so be looking for another Zoom invite for that meeting as well. Anybody have any questions before I hand it over to Ken?
Hey, Tim, I think your microphone dropped off.
Oh, I'm sorry. Over here.
Yeah, it sounds like you're far away. Yeah.
Okay.
He is.
I'm not better. Yes.
He's in California. It's a long yell.
Could you hear me, or should I repeat what I said?
We heard you. It was just like you were talking inside a milk bottle, if you remember those. Okay.
A milk bottle. Okay. All right, Ken, you want it?
Yes, Sari Buckaroos. Okay,
All
again,
right.
thank you. And I want to underscore the praise that Frank Melillo has received. Those images were absolutely stunning. You did a great job on that solar presentation. Rick Hill is lucky to have you as one of his supporters. So congratulations on that. Okay. Our next
observations are in every report.
Pardon?
His observations are in every report.
Yeah. Yeah. Okay. Okay, here we go. Greg Shanos, not to be confused with Santos. That's another person we don't talk about anymore. Greg Shanos resides on Longboat Key, a small barrier island off mainland Sarasota, Florida.
Oh, wow.
Who's got a lot of time on his hands if you've seen all of the things that he contributes to the aLpo. His interest in astronomy was sparked when he first observed Halley's Comet back in 1986. What were you, 17 or something back then?
No, 27.
27. With the advent of electronically assisted astronomy, he became interested in planetary astrophotography. Having heard that the aLpo organization actually archives and scientifically analyzes amateur astronomer images, he himself began submitting his own planetary images and soon became a member of our fine organization. Deep sky astrophotography has always been out of reach for him since it involved very expensive equipment, taking long exposures for hours and time-intensive post-processing of the frames to produce even a single deep sky image. That's why we call them faint fuzzies. The smart scope revolution has changed all of that. The equipment today is now affordable, compact, and really easy to use. A Hubble-like image appears on your own cell phone, or can appear on your own cell phone within minutes. A dream comes true. So right now, as you see on your screen there, Greg will discuss the ZWO SeeStar in particular, and how it has revolutionized amateur astronomy. And you got a half hour, fill it. Thank you very much, Greg.
Thanks, Ken. Can you all see the PowerPoint?
Yes.
Okay, I can't see myself next to it.
Yeah, Microsoft 365. Okay. There you go.
All right, so first, I'll go through these slides rather quickly. So what is a smart scope? A smart scope combines a telescope, a camera, a tracking mount, and a computer into a compact portable imaging system. So the first ones to come out were the Unistellar, pioneered the smart scope revolution. And these are 3-inch mirrors, and the EV Scope 2 is a 4.5-inch mirror. Another French company called Vaonis also came soon after. And this one, the Hestia, this is just a telephoto lens, essentially. Just place your cell phone on it, and it's only good for the moon and the sun. It's not really good for deep sky. But you can see my cursor, right? Can you see my cursor?
Yes.
Okay, good. And the Vespia series here has a 50 millimeter lens, which is the same as the SeeStar. So this one is basically, these are basically equivalent to the SeeStar, and they have a 250 millimeter focal length, but the chip is larger. It's 8.3 megapixel. The Stellina, and I actually saw the Stellina in use during the annular eclipse expedition. One of the members had it there. This has an 80 millimeter lens with a 400 millimeter focal length. And the Hyperia, this one is wild. This one is has a 5.9 6-inch apochromatic lens at the bottom. It over 1,000 millimeter focal length, weighs 165 pounds, is 7 feet in height, and has a 61 megapixel chip and costs $45,000. I kid you not. So these are around 3,000 to 4,000 here. Now the Celestron Origin, which is not out yet, uses a mirror, and it has a RASA system, which is a Rory Ackerman Schmidt Astrograph 6.4 megapixel chip, and it's f2.2. So this is really fast, and the chip is in front. And one of the great things about the Celestron Origin is that the chip is interchangeable, the CMOS chip. So when a better chip comes out, you just send this back to Celestron, and they will remove the old chip, put the new one in, calibrate it, do the dark frames, etc. And now you telescope. So isn't that fantastic? So you don't have to dispose of the, because once a better model comes out, you don't want to use the old one. Now, you know, the mirror and the telescope itself, the CMOS chip is the heart of this. And then the most affordable here, and the price has dropped now from $499 to $449, are the Dwarf and the SeeStar. And the Dwarf is slightly larger than a VHS cassette. And this one came out first, and this has a telephoto and the Dwarf 3 is coming out, and I'm going to buy the Dwarf 3 because it's going to have internal filters, and this has a telephoto as well as the telephoto's 50 degrees. The telephoto's 3 degrees wide, whereas the wide field is 50 degrees wide. So this is a really wide scope. And then the SeeStar, which I'm going to talk about in detail. So just to note, this is not an advertisement for the ZWO or the SeeStar. This is the one I own, and this is the one I'm familiar with. So that's why I'm going with this. It's portable, automated, inexpensive, and it's controlled with your cell phone or iPad. You need to download an app to start it, and it's a credible potential for citizen science education and research. The software firmware is updated at least once to twice a month, and support is excellent. If you send them, they listen to their customers' requests. If you send them an email, they'll respond to you within 48 to 72 hours. And there's excellent, this is the official ZWO Facebook group, and ZWO actually watches this. So if you post something, the company will see it. And then Kai Young, which I'll mention later, has his own called the Smart Scope Underworld. The Smart Scope has gone underworld, but I'll talk more about what he's done, which is really amazing. And I also have a podcast on the SeeStar in the April 2024 of the Observer's Notebook. I did that with Tim Robinson. And as Dave Teskey mentioned, I also have an article I had written for the Lunar Observer. So the SeeStar has impressive specifications. It's 50 millimeter 2-inch apochromatic triplet optics, which is excellent. Focal length is 250 at f5, so it's relatively fast. The chip is a 462 CMOS color chip, and this is, here it is here, and this is actually the same chip that's in my ZWO 462MC, which I use for all my one-shot color planetary images. So when you see the images, they'll look rectangular, and it's because of this chip. So it's only 2 megapixel, but it's still pretty good. And Altaz motors, images are dithered. Here's what dithering is. It has dark UV, IR cut, and also H alpha and oxygen 3 narrowband filters, autofocuser, has a dew heater included, because that's fantastic, especially in Florida. Carbon fiber tripod, solar filter, USB cable to connect it to your computer in a carrying case. All this for $449. Incredible. And then these are recommended accessories here. You don't need any of these, but the two that I would really recommend is this one and this one, because what happens is, in order to calibrate this, you don't even have to point it north. All you have to do is spin it around, because it calibrates a compass, and it'll tell you, okay, when it's done, and then you have to level it. Then you're good to go. That's all you need to do, period. Okay, so these two really help. This is also very helpful because it blocks out ambient light that would be coming in. So that's really good. And then I like to use an iPad instead of an iPhone, because, I mean, look at the difference, you know. you have this little thing as opposed to this big. So it's much better to have an iPad. And I found that if you get the 10th generation, which is only from 2022, it costs $449 on Amazon as opposed to like $1,200 that the current iPad would cost. So, and it works perfectly. So get at least the 10th generation. It costs as much as the SeeStar. And then this, you don't need it if you're up north, but it reflects the sunlight really well. It gets very hot in the south in summer. It's like 92, 94 degrees, and the heat index, the feels like temperatures like 115. So it's very brutal doing solar astronomy in the summer in the south, as Dave Teskey will attest to. And then Astromania, these are vibration suppression pads, okay, which help because if you're walking around, it'll jiggle it a little bit. So the only two things, and then it's better to have it a little bit higher rather than this little tripod stand. But, you know, these are the recommended accessories. So here's the main screen. And I saw that there's a beta version coming out, should be out in August. That's going to be a major upgrade to this. They're combining these three into one called solar system. So you'll just see stargazing, solar system, and scenery. And then, so this is the main interface on your iPhone or iPad or Android phone. It works on Android too. And what happens is there's a sky atlas here, and it also tells you your local weather, the moon phases, once it's connected to the internet. You don't need to be connected into the internet when you're in the field. It works by Bluetooth. And images are placed here, and then Deep Sky Stack will allow you to stack the images too, but it's best to use some third-party software. And it also talks to you. It has a synthesized voice. It says autofocusing, a digitalized female voice to boot. Object is centered, etc. It's really cute. And then all images that I'll show are taken by me straight out of the camera unless otherwise stated. So I didn't do any post-processes, so you can see just how great the right out of the camera images are. So first thing, scenery, you just press this, this goes up, you hit the autofocus button, there it is, hit that, and you have a picture. And you could also take a video too, okay? This is only the second time I've ever used scenery mode. I never use scenery mode, but it's there. Lunar mode, just hit the moon and it goes to the moon, and you have here's how it appears. This is actually a screenshot of the interface here, and then you have a 2x and a 4x, so you can have it magnified, which is, now this is digital, it's not optical, okay, zoom. And then you press the raw here, and it takes both AVI and MP4 images. AVI are uncompressed, and those are the ones used for AutoStacker and AstroSurface. And they're limited to 10 minutes. And there's also a time-lapse feature right here. So you could have one image taken every 5 seconds, every 10 seconds, every 60, and it makes an MP4 movie. So it's really, really nice. And then send your lunar images to David Teskey. Will this still be the official email? And now that the website is changing, that may change. I don't know. But for now,
yes, it will.
It'll stay the same. Okay, fantastic. So I'd like to thank Dave Teskey for actually getting me interested in lunar imaging. And here there's something called the Lunar X and V, which I was actually able to image on June 14th. And if you look very closely, there's the V and there's the X. And if I zoom in 2X, and if I zoom in 4X, can you see it? There's a V and there's an X. Now, these are single snapshots from the SeeStar. And then what I did is I imaged it with a Meade LX200 GPS 8-inch. I did it with this, but for some reason the X got cut off. But the Lunar X and V is an example of pareidolia, which is when a meaningful image and a random visual pattern. So you know how as a kid you looked up at clouds and said, oh, that looks like a bunny, that looks like a dragon, or the face on Mars. Remember that back in the 70s? Your mind makes a pattern out of something that really isn't there. So this is the lunar V, and the V forms from this crater Euclid, and the X forms actually from a combination of these three craters. And what's really cool is this lunar X and V is really predictable. So the next one is going to occur on August 12th at 1 hour 30 minutes UT, and this is published in the Lunar Observer. And be careful, because this is universal time. So the time Eastern time will be, New York time will be August 11th at 9:30 p.m. And use WinJupos. There's actually a local time and a universal time clock there now. And I lectured to John Silason's group, the Astronomical Society of Greater Hartford, which I'm also a member. And I looked at WinJupos and I said, and I was explaining what I was explaining now, how to convert UT to local time. I said, wouldn't it be nice if WinJupos had local time too? So I emailed Grisha Han, who's the developer of WinJupos, and asked him if he could do that. He said, fantastic idea, and he did it. So that's my small contribution to WinJupos, is the local time in addition to universal time, which I think is important, because I have missed events thinking if you go out on August 12th and try to look, it's gone. It has to be your time, local time, which is actually the day before. So be careful of that. Penumbral eclipse. I did a penumbral eclipse. Look at that. You can see the shadow. This is just a single shot, mind you. This is not processed. This is just, I just clicked on it and it took a single snapshot. Look at that nice resolution. And the next actual, there'll be a partial lunar eclipse on September 18, 2024, but only 10% is going to be eclipsed. The next total lunar will be March 14, 2025. So I'm looking for, so 10%, I'll take it. I want to be out there imaging it. Oh, and also what's interesting is August 11th is actually into the 12th, going to be the peak of the Perseid meteor shower. So I'll be out imaging the lunar X and V, and then I'm going to pack it all in and start observing the meteor shower for Dr. Lunsford. So share the love. Okay, solar mode, same thing as lunar mode. Here's a individual snapshot, and then 2x and 4x. Look at that. This is just this is a screenshot of the screen of what I'm looking at live. It's amazing. So same thing, take a raw image, and actually when I did this, it's so serendipitous, because Frank Melillo spoke about this AR3664. I was doing this during the Great Carrington event sunspot. I didn't know it at the time. Look how nice that came out. Now this is processed. So Frank, you want a telescope that gives you the whole image of the sun? The SeeStar is it, man. Look at this. And then
yes, the whole, that was great. The whole, I only get part of it. I can't even get the whole image.
Well, the SeeStar will give you the whole thing. Here's the whole thing. Just a single
that's a great shot. Yeah.
Yeah, and look at that. Here's a single snapshot, right? And then here it is with a 3-minute video lined and processed with AutoStacker. And then here's an image with the SolarMax 2 that I have. So this is H alpha. Look at all those flares going on in the sunspot group. It's amazing. And this is,
we don't usually use whole disk in the reports, solar reports, because they don't reproduce well in the journal.
Oh, okay.
So we use the close-ups. That 4X was beautiful.
Oh, yeah. Yeah, isn't that nice? Yeah.
Yes.
And then, and I remember on this day, I was out on the May 10th. I was out doing a outreach with the local group of deep sky observers down here at the Bishop Museum and Science Center, and it was very, very hazy. But that was the day that you could see the auroras all the way down to Key West, and with all the light pollution, the city of Bradenton, we didn't see anything. But it was cool that, I imaged this right at the time that this was happening. It was serendipitous. And then, of course, the solar eclipse of April 8th, 2024. My wife and I went with a group, 400 people to Uvalde, Texas, and we completely clouded out. So it was really bad. But here's some images from people using the SeeStar. Look at that. Jeff Patel actually had a airplane going through it, and our own Tim Robinson caught it here. So Tim, when you took the solar filter off, did the SeeStar automatically refocus and have everything in perfect contrast?
That telescope is amazing. I took the
So it
filter
did,
off,
huh?
It refocused and it started shooting. I gotta tell you, I'm not an astrophotographer by any sense of the imagination. The very first photograph I took of M42, I've been doing astronomy since 1972.
Yeah.
The very first photograph I took of M42 was the day I received this telescope. Took it out of the box, put it on the front patio of my house.
Yeah.
Aligned it, went, hey, where's M42? Went, took a picture. 10 minutes later, I had a beautiful image on my iPad. This thing is
like a Hubble-like image, right? Yeah. It was incredible.
Then I went to the Horsehead. And I took a picture, and people, a 50-millimeter telescope can't take a picture of the Horsehead Nebula. Yes, it can. No.
I have images of that coming up
from your couch.
Yeah.
I was sitting in my living room watching the Dodgers, and I had my iPad. And I leaned over to my wife and said, "Look at the picture I just took." She goes, "With what?" I said, "The telescope out on our patio."
Yeah.
Dolores says I'm cheating.
The important thing here for solar eclipses is once you take the solar filter off, that you're not wasting time like adjusting contrast and brightness here and refocusing and all that. This did it all automatically, and it's perfect. And of course, being a smaller C rectangular, you're only getting the inner corona, but that's fine. It is a diamond ring, all right? And but it's not a planetary scope, okay? And it's not because of the price, it's physics. Any telescope, even a $45,000 one, if it has a 250 millimeter focal length, it will look this small, okay? And then this is with the 2x and this is with the 4x. But it's still good because you can see the belts and zones of Jupiter there. Isn't that cool? And if you overexpose it enough, you'll see the 4 Galilean moons. And Rick Hill sent me this. He has the Unistellar. So at the end, Rick, tell us about the Unistellar. I'm curious to see, because this is a $4,000 or $5,000 scope here. And then
I
notice,
didn't pay that for it. I got it on eBay. There's a couple of them on eBay for $1,200 right now.
Oh, wow.
I got mine for $900, and it turns out it was brand new in the box. The guy had never used it, and everything was still wrapped in the plastic.
Oh my God, that's serendipitous. Yeah.
Yeah, for $900 you can't say no.
Yeah.
And I just calculated the day when Uranus and Jupiter would be close.
Yeah.
And it turns out they were just inside the field of view of the telescope. And so I got the conjunction really nicely.
So that gave me a great idea. Conjunctions of planets would be a good thing for the SeeStar to do. And I think there's one coming up in August for Jupiter and Mars. I forget the exact date of Saturn.
Conjunctions with the moon.
August 14th, I believe.
August 14th, yeah. They're going to be like 20 arc minutes, which is a quarter quarter of a full moon diameter. So they'll fit in here. This is 0.72. So,
but also planetary conjunctions with the moon.
Yeah,
really good.
Planetary conjunctions with the moon too. Yes, exactly. So you could still use it for planetary. Okay, so here's some of the images that came through. Like Tim Robinson was talking about. Look at that. M46, 36. Now, this is more than 36 minutes because it's only stacking the best ones, okay? So it rejects it. It'll tell you, rejected this image. So you take 10-second exposures. Now, when the SeeStar first came out, it only did 10-second exposures. And now it's been expanded to 20 and 30-second. I've never had any luck with 30 seconds, so I never use it. But 20 seconds works beautifully, and I'll show you some 20-second images. But I like M46 and Puppis because you have a planetary nebula within the isn't that cool? And then this is the double cluster between Perseus and Cassiopeia. You can fit both of them in there. And then this is M7, which is a Scorpius in the heart of the Milky Way. And if you look really closely, you see dark lanes here. See them? This is like a whole dark area.
Oh, yeah.
With the Unistellar, one of the first things I did was see how faint I could go. And I did the Leo triplet for 1 hour.
Yeah.
And I got 19th magnitude with a 4-inch
Oh
telescope.
my God. Yeah. I'm getting about 15th magnitude with the SeeStar. And then here's M13, M23, and here's M22. And this is in Sagittarius. This is in the heart of the Milky Way. And you can see some dark areas here too, and that. So for the brighter stars, open and globular star clusters, don't go 20. Do not go 20 because I find it will overexpose and things will like bleed out, you know. So you get that star bloat. So you want to use 10 seconds for clusters. And there's a faint galaxy right there too. And
the
then
contrast is very good.
for planetary nebula, 20 set. Look how round the stars are. The tracking's perfect, and they have a nebula filter. So and it goes on by default. So here's the M57. Here's M27, the dumbbell, and then here's the owl. Okay, and then look at this. The nebulizer. Here's what Tim was talking about. Look at the horse head. This is 41 minutes. Look at that. And these are not processed. This is exactly what you are seeing on your iPhone or iPad or Android phone. I mean, wake me up. I must be dreaming. You know, this is a dream come true. And this is Aldetech. Look at the Orion Nebula, 46. And then this is the Running Man Nebula here. And then this is the Lagoon Nebula and Sagittarius. Look, doesn't that look three-dimensional? I mean, it's amazing. It looks three-dimensional with a little 2-inch piece of glass. I mean, just unbelievable. And then galaxies, like I said, use 20 seconds for the fainter. And look at that galaxy. You can see the spiral arms coming through, and it doesn't overexpose the core, which is amazing. So M81, M82, this is Bode's galaxy and the cigar. And look at M33. This is a very, very, very low surface brightness. His face on, look how nice that came out. And then M51, the whirlpool. Everyone loves the whirlpool. And then another thing you can see are quasars, which are active galactic nuclei. And one of the best ones you can see here is this one here called Marcanian 205. If you go to Spiral Galaxy NGC 4319, it's the one right next to it there. Isn't that cool? And then look at that, supernova remnants, the Crab Nebula, and the Veil Nebula. Now, these are actually 10-second exposures because they were from 2023. This was before the upgrade that they could go more. But look, for 10-second exposures, I'm going to reshoot these at 20. These are going to be even brighter and nicer with 20. But look at that. Isn't that amazing? Now, here's the field rotation effect. Since you're in alt-az, you get the field is rotating around, but the software undoes the field rotation. But sometimes if you're greater than like 45, 50 degrees, you get around 75, 80, close to the zenith, the field rotation becomes more significant. And this is what the field rotation is. And people have done tweaks to be able to have the SeeStar in equatorial mode. I'll talk more about that. But, you know, this doesn't really bother me because if you're going to post-process this, first thing they tell you is always get rid of the very edges because there's always artifacts around the edges. So the rest of it is perfect. So I'm not too concerned with that. And then SeeStar is also a self-contained post-image processing instrument. So here's the sun, and you can process it within the SeeStar and the iPad yourself. So this is how it looks, and this is how it looks after I sharpened it. And then this is with auto stacker and registacks. Look at that. It looks virtually identical, doesn't it? But the only caveat is if you use the SeeStar software, a 3-minute video takes 30 minutes to process. A 3-minute video here took 3 to 5 minutes to process. So you're looking at 3 to 5 minutes versus 30 minutes to process. So, but a lot of times I just let it run and it's fine. And then here's the moon, the same thing. And look, the SeeStar actually did a better job of aligning and stacking than AutoStacker. Look, this looks blurrier. This looks sharper. The initial just align and stacked image. And then once you sharpen it, they're pretty much equivalent. But the same thing with the moon. It takes 30 minutes with the SeeStar software.
With Unistellar, it co-adds all the images on the fly.
Oh, wow.
So when you're done with your exposure, there's your final product.
Oh, wow, that's nice. Well, maybe that'll be a nice upgrade for the SeeStar later. Now, I found out there's this excellent program called Cirrel, and here's the website. It's free, and it stacks the FITS images. And there's this one guy, Rich, he has a Deep Space Astro as his handle on YouTube, and I subscribe to him, and he's got 40 tutorials that goes over every single aspect of how to use Cirrel. And I looked at one, and they even have written a new script specifically for processing light FITS files from the SeeStar. So
Hey,
this is fantastic. Yeah.
Right. Can you start wrapping it up a little bit?
Oh, okay. So then what? And so here's an example. Here's the straight out of the camera. Here's the SeeStar, and then here's Cirrel processed. Isn't that amazing? So it really can make it pop. Okay, and then also you can do research with supernovae. This is a type 1 supernovae. Here's a type 2 supernovae, and then comets are fantastic. It will once you're connected to the internet, it will let you know which comets are out. You hit it, and then here's a faint comet, 13.8 magnitude right there. And then here's comet Pons-Brooks. Oh, one thing I forgot to mention, the SeeStar also will identify every single image, every single galaxy or deep sky object within the image. I think that's a great feature. And then here's Pons-Brooks. And then when I was imaging it on this night, I noticed that the nucleus was overexposed where it wasn't here, and I didn't know why. And then I found out that it was actually an eruption. So it wasn't, it actually identified something. So this is real physically. Wow. And then there's this other great comet, Chuchi-san Atlas, that already has a nice tail, and this should be available. Will be visible in October 2024, so this will be incredible. And then you can also try doing asteroidal light curves with the SeeStar. This person did it here on YouTube with this, and I tried it here. I only got about 13%, just a little bit here. And then you can also do photometry of a variable star. This was done by someone in the Facebook group. Look at that. And then spectroscopy, you can buy a $7 diffraction grating. Make sure it's a 50 line per millimeter. Tape it on. This is Vega. And then you have to go slowly down. And here's your spectra. So here's 400 to 700 nanometers. And then what I did is I took and added the filter, the oxygen 3 and H-alpha filter. And look at that. This is the oxygen 3 right here at 500. And here's at 656. the H alpha, and it blocked everything else out. And then what I did is I put the light pollution filter. So this is blocked here. This is blocked there. That's blocked there. That's blocked there. And then this is it. This is coming through. This is coming through. That's coming through. That's coming through. And that's, isn't that amazing? So this is blocking sodium and mercury lights, but those are going away now. We got to get filters that block LED lights. So that's another animal. And then right now there's a big nova that's going to happen, T Corona Borealis, that's supposed to go nova any day now. Now the big difference between a supernova is the star totally explodes, and a nova, the star is left intact. But go take the SeeStar and go IC 4587, and then it identifies it, and the next nearest star right there is T Corona Borealis. And the next upgrade I saw in the beta version, the SeeStar, you'll be able to manually enter your own right ascension and declination coordinates, and it will slew to it. And the mosaic mode is also in progress. So there's a lot coming up. So this is what mosaic mode is that it doesn't have yet. See how the edges are cut off here? And so mosaic mode will move it, and it'll stitch it all together. Notice the nucleus is not overexposed, and this will really pop just like the Lagoon if I were to post-process it. And then Kai Young has the Smart Scope Underworld. He's developed a special app for Windows that you could download for free that allows equatorial mode of the SeeStar, mosaic modes, and you can run up to 5 SeeStars at once at all different objects. Isn't that amazing? So he's taken this to a whole other level. And so these conclusions I basically said already. So please drive carefully. There just may be a SeeStar on board. Thank you. Okay.
Major thanks. Major thanks. Everybody, get out your wallets and leave them at the door. Okay.
Yeah. So if you're ever on the fence about, should I get a smart scope or not, I hope I pushed you over the fence. And everyone runs out by not necessarily a SeeStar, but a Veronis, a Unistellar, a Celestron Origin, any one of them. But
okay. Thank you again. Richard, are you ready?
Yes, I'm ready.
Okay, for those of you who don't know Richard, and I don't know how you cannot know Richard, as I said yesterday, I'll repeat this, he's another, quote, ball of fire, unquote. Though we don't know how much longer he can keep this pace. He's currently the remote planets section coordinator, the Jupiter section coordinator, the photometry coordinator for the Mars section under Roger Venable. He's a sitting aLpo board member, as well as a professor at Gordon State College, which is just southwest of Atlanta in Barnesville. He's authored various books and scientific papers, Lions and Tigers and Bears, oh my. Richard, you got to start looking after yourself. The only question I have, now your talk is going to be on Jupiter in 2024, but in just 25 or 30 words, what drew you to remote planets as a section guy, and what drew you to Jupiter as the section guy? And then you got a half hour.
Well, I was appointed coordinator of the remote planet section back in 1990 by Westfall, John Westfall, and I realized the big area I could do was photometry. And so that appointment led to photometry, and most of my talks are on that subject, although the one I'm going to give is not. Jupiter, well, I can remember way back in the 1980s, I think the first target I looked at with my 4-inch telescope was Jupiter, and was in the middle of the night. And I know one night a police officer came to me. It was about 2 in the morning. And he said, I don't want you to go anywhere because somebody robbed a store and you fit that person's description. So I didn't go anywhere. Fortunately, whatever happened, I don't know to the case, but I didn't end up being charged with something I didn't do. So that's my little story on the remote planets in Jupiter. So today what I want to do is I want to talk about some highlights of the 2023-2024 Jupiter apparition. This basically covers the time period from May of 23 up until the end of April this year, 24. So in the next slide, I want to talk about, first off, make a few introductory remarks about Jupiter. And again, I want to point out, I'm going to be asking the audience a couple of questions. So, you know, you might want to be ready to unmute when I ask you. And so anyway, first question I'm going to ask you is, how many people have seen Jupiter since, let's say, June of this year? June, raise your hand. June or July. Okay, a couple of people. It's up in the east. It's actually pretty high up, you know, 30 minutes before sunrise or 45 minutes before. So it's pretty good. So, okay, now this slide is a picture of Jupiter taken with the James Webb Space Telescope in infrared light. Now, can we see infrared light? No. We can't. We can see invisible light. But anyway, it's a very interesting picture. North is near the top. Of course, what do you see in the lower right-hand corner? I can't hear you.
Great red spot.
Great red spot, yes. And I'm afraid great red spot may be a term of the past. So listen up and let me explain why I said that. But anyway, I'm going to talk about the great red spot today. And then I'm going to also talk about oval BA, which is on the other side of it. I don't see it here. And so anyway, in the next slide, let's go ahead and focus on, we skipped a slide, but anyway, that's okay. That's okay. These are 6 close-up pictures of the great red spot taken during 2023. The last one is 2024. 3 big parts of the great red spot. The outer, sort of dark brown area is sort of the wall. Then you have sort of an orangish interior, and then a very dark center. It's kind of like, how many people have had a Cadbury Easter egg? Really good, by the way. They're really good. You got the milk chocolate on the outside, you got the white in the middle, and you got a caramel center. Really good. I highly recommend it. But anyway, kind of reminds me of that. And I want to ask you a question, though, everyone. I've been doing some work on the great red spot. How many people remember when they said you can fit an Earth or 2 Earths inside of the great red spot? How many people remember that?
I do.
Okay. That's kind of like, that phrase is kind of like bell bottoms. They kind of went out of style in the 70s, right? Great red spot can no longer hold an Earth. Let me explain in the next slide. Okay. Now I've been measuring the length, the east-west length of the great red spot. This is a graph from 8 degrees up to 20 degrees. Now just sort of imagine a degree on Jupiter is roughly 700 miles. Okay, just put that number in your mind. Okay, 700 miles. Length of Texas, maybe. All right, we go from 2014 up to 2024. What trend do you see? Is it getting bigger or smaller? This is east-west length.
It's getting a little smaller.
Yes, that's the key, a little smaller. And sometimes it even gets a little bigger and then it gets smaller, kind of like 1 step forward, 2 steps backwards type of thing. And what's causing this? Well, I know back in 2020, back when we were going through the COVID thing, the great red spot actually was throwing off red flakes. And John Rogers was probably one of the first ones that pointed out that the great red spot actually shrunk quite a bit when it was doing that. It did stop doing that and it rebounded a little bit. And I talk about it in my report. And of course, John Rogers puts out some excellent reports and he talks about it as well. So the Great Red Spot over the last decade has shrunk by something like quite a bit, like 3%. Of course, that's not a whole lot, but over a century, that's very significant. So let's take a look now. Let's compare what the Great Red Spot has done over the last 10 years compared to over the last century in the next slide. Now, from 1927 to 2017, the Great Red Spot shrunk at a rate of about 0.2 degrees a year. So multiply that by 90, and you get quite a bit there. 0.2, 1.8, 18 degrees, I think is what you get, or something close to that, which is substantial. During the last decade, it's shrunk by about 0.3 of a degree per year. Now, again, a degree is about 700 miles. So it's shrunk by something like 300 miles a year. This is east-west every year. Now, 300 miles is actually kind of small when you compare it to Jupiter. But again, looking at stuff over time, we can come up with these trends. Okay, you can't do it over 1 or 2 years, but over 10 or 20 years, yes, you can. And what's perhaps even more shocking is the shrinking may be accelerating. Now, to put things in perspective today, the Great Red Spot is about the same size as the Earth. The east-west length is a little bigger than the Earth. It is something on the order of 8,500 miles. Now, the Earth's diameter is roughly 8,000 miles. Okay, so east-west length is a little bigger. North-south dimension, though, for the Great Red Spot is only 6,300 miles. The Earth's diameter is what? I just told you, about
8,000 miles diameter.
About 8,000 miles, yes. So the Great Red Spot, actually, if anything, may even be a little smaller than the Earth, if you subtract the two and, do the formula for an ellipse. So the Great Red Spot is getting smaller. No, you can't fit an Earth inside of the Great Red Spot anymore. All right, well, let's go on ahead. The Great Red Spot's the biggest spot on Jupiter. What's the second biggest storm on Jupiter now?
That would be Oval BA.
Oval BA. Now, can anyone tell me when Oval BA started? I want a month and a year. First off the year.
I think it's 1941. So somewhere around 1941.
That's when things very first started. Then you had 3 ovals, and then went to 2 ovals, and then we went to 1 oval. When did we go to 1 oval?
Like around 2000, 2001?
2000. You got it. Who said 2000?
Jim.
Let's give him a hand. Yes. March of 2000. So next March will be the 25th anniversary of Oval BA. Now, what I've got here are 5 pictures of Oval BA taken from July in the upper left down to February in the lower right. What difference do you see between the first 4 and the February image?
Disappeared.
Yes, it doesn't show up. Now, I am waiting to see what the latest JunoCam images are. As of December, Oval BA was still visible, although this is with JunoCam, which is probably a lot better than Earth-based images, but Oval BA sort of did a disappearing act here. And that's not the first time it has done that. I've had trouble seeing Oval BA in previous integrated light images. All right, so Oval BA, what could have caused this change? Well, actually, let's talk about changes first. In the next slide, we've got a couple of changes here I want to point out. First off, the dark border grew lighter. Notice the dark border is what allowed you to see Oval BA. Okay, that went away. Everything's the same intensity. You don't see much except in methane band light. Now, the dark belt to the left did fade away. And what's possible cause of the change? Again, this is just a possibility. Oval BA did pass the Great Red Spot back in late October. What I'm currently looking at is Oval BA getting bigger? And we know the great red spot's getting smaller. And again, wait and see, stay tuned. I'll have an answer for you someday, probably next year. We're already working on it for the Graham meeting in October. All right, so that's a little bit about oval BA, and I want to talk about drift rate. Now, folks, watch my finger. What we do is we measure how fast oval BA moves relative to the magnetic field of Jupiter. Fast drift rate, slow drift rate. Okay, do you get the picture? Fast, slow. The more negative, the less negative. Okay, do you understand? Now the graph here on the vertical axis, I have the drift rate. Again, it goes from 0 up to -18. -18 means it's moving fast. 0 means it's moving slower. Then I've got the year plotted. What trend do you see? What's the trend?
Well, it's increasing.
It's increasing,
Okay.
spinning faster. Yeah.
Yes, it's moving around Jupiter faster, and this is something that I find sort of interesting. Way back when, about 20 years ago, it seemed like oval BA would go faster when it was, I believe, far away from Jupiter than when it got close. I mean, when it was far away from the great red spot, and then it changed when it got closer. But now what I'm finding out, it almost seems like it's sort of taking off. Again, I've got a graph on that. I'm not showing it today, but this is going to be another talk for another time. I want to go into more detail. But anyway, oval BA does seem to be moving faster. Now, a third change on Jupiter in the next slide, and again, this is probably only for CCD. Okay, yeah, it appears increasing. Okay, it's not clear what's causing the change in oval BA. Now, let's go on to the next slide, which shows some curious little white spots, just several of them. I noticed 10 or 20 of them. And this is picture taken in November of last year. And I just felt as though these were very interesting. They're about 2,000 kilometers across. And so in the next slide, I summarize some statistics on them. The mean size is 2 degrees east-west. Again, a degree is about 700 miles, we'll say. So 700 by maybe 800 miles. So about the size of Alaska. Each one of them about the size of the state of Alaska. Mean latitude's almost 10 degrees north. And the drift rate's pretty fast. It's a system 2, so it's going quite a bit faster even than oval BA. Oval BA was around -17, so these are going even faster. Right now, how many people remember what happened on February 15th, 2013? It was related to astronomy. Anyone remember that? What happened on that day?
The asteroid hit Russia.
Yes. About a 20-meter object hit Chelyabinsk, Russia. And well, it's not, these objects are not just hitting Russia, they're also hitting Jupiter. So let's take a look at the next picture here. And you can see a flash developing. This is a very bright one taken, I believe this is the one taken in August, but I may be wrong. So, but anyway, you can see how it's starting to come. And then you can see all of the light here. Now, if the Chelyabinsk event happened on Jupiter, it would probably be about as bright as this spot on the left. But look at the spot on the right. How does it compare? I think it's 100-fold brighter. So 4 of these flashes were seen. I believe the one of them was August 28th, November 15th, and then December 28th, 29th of last year. We had 4 flashes on Jupiter last year. More than likely, these are impacts. And in my apparition report that I just submitted last week, I think, I present some more evidence of that. So let's take a look at some facts and figures here. A total of 13 flashes have been imaged from Earth on Jupiter since 2010. That's about one a year, actually. 7 events in the northern hemisphere. Actually, this should say 5 events in the southern hemisphere because one of them was right at pretty close to the equator. So they're about evenly distributed between north and south. But what I've found out is they're more likely to occur when Jupiter is closer to the sun. Now, what lies between Mars and Jupiter? I can't hear you.
Asteroid
belt.
Exactly, the asteroid belt. Could it be these impacts are more frequent when Jupiter gets closer to the asteroid belt? I think more observations are needed. I mean, this is very preliminary. One thing that I kind of felt, or I mean, kind of was surprised at, the luminosity. Now, luminosity's total amount of light given off. Remember, Jupiter's a little farther away than some of the viewers in Russia were when they imaged their event. The luminosity is about 2 to 60 times that of the 2013 Chelyabinsk event. So quite an amazing event. So finally, in some conclusions in the next slide. The Great Red Spot is continuing to shrink. We will see what happens to it as time goes by. Oval BA appears to be moving faster. Now, I cannot tell you whether it's getting bigger or smaller. Just some preliminary results seems to indicate that it's about the same size. But again, that's very preliminary. I need to really go back and look at some things and make sure I'm making consistent measurements. We did have an outburst of tiny bright spots in the north equatorial belt. And Jupiter flashes more likely to occur when Jupiter is near the sun. And finally, very important slide, last slide. Very important. This one, I can't do it without people who have submitted images to the aLpo Jupiter section coordinator, and also to Jim Tomney, who is organizing our archives. I mean, it just makes life so much easier if I could just go to an archive and take my measurements rather than go through my email and whatever. So I want to thank you for your attention, and I'm willing to answer any questions you have.
Thank you, Richard. Thank you, Richard.
Yeah.
You're welcome.
Yes, Rich, when
Yes,
you mentioned, when you mentioned about when Jupiter closer to the sun, you mean when Jupiter reached perihelion to the sun? Oh, not as close to the sun as seen from Earth. That's not.
No, yeah,
not really.
it's
Oh,
close
okay.
to the sun. Yeah, Jupiter actually was a perihelion. It was very close to perihelion in late September 22. I think it actually hit perihelion in January of 23, but obviously Earth was further from Jupiter in January than was back in September. But yeah, Jupiter's still very close to perihelion, and in 5 or 6 years, it'll be at aphelion. I'm predicting we're going to image fewer flashes. But again, we'll see. The technology is going to get better. I mean, obviously, the SeeStar, which we just heard about, they're going to come up with a better version by then, I think. And I think people are going to be imaging a lot more flashes.
Okay. The Great Red Spot. Now, we first saw that 300 years ago, right?
Well, I don't want to say 300. John Rogers' book, he does a good job of documenting. We're certain from 1870. So we're certain of 150 years.
Okay.
There were some observations in the 1830s. But what about 1840s and 50s? I don't know. And then 1600s, there was some observations. But unfortunately, the whole 1700s, 100 years,
right,
people didn't observe, or they didn't publish their drawings.
Okay.
Thank you, Richard.
You're welcome.
Thank you. Thank you. Let's move along. And those of you that have questions for Richard, I guess you can email them, or he doesn't take phone. Well, he takes phone calls, but that's another story. Our next presentation is with John O'Neill. Now, I had solicited all my speakers to send me little biographies about themselves, but I guess John didn't get the email. But I've met John because he was a nice speaker at the Peach State Stargaze last fall, weren't you, John? John O'Neill? Is John online?
There I am. Okay, I'm unmuted now. Yes, I've spoken at Peach State several different times over the years.
Right. So I didn't get the bio on you. So what I'm going to ask you to do is, can you tell us where you live? Well, you live in North Carolina. Tell us a little bit about yourself, how you got into astronomy, how you got into aLpo, how you got into eclipses. You got a half hour. Let's take it. Go right ahead.
Okay, thank you, Ken. Hello, everybody. Thanks for attending the conference, and I hope everyone's been enjoying the presentations as much as I have. I've learned a lot yesterday and today. So I've been into astronomy since I was a kid. I remember at 14, 15 years old going outside and looking for satellites in the sky, because that was a big thing back then. John Glenn was from my native state of Ohio, and I thought, well, gee, if John Glenn, a guy who lived right down the road from me, could become an astronaut, that got me excited and going. And when I turned 18 years old in the mid-70s, I joined the Black River Astronomical Society. You may be aware of them, Ken. Just down the road from you a little ways. And one of the perks of being a membership is the club had a subscription to the Strolling Astronomer and was a member of aLpo. And we had a library in our cooling off room, we called it, next to the observatory. And we would go out there, and if it got cloudy or if we were imaging and letting the camera do its thing, we would go in the library and read. And so I've been enjoying the Strolling Astronomer for many, many years. I'm currently an associate editor for Amateur Astronomy magazine, where I write articles about the sun and solar activity. And I, along with Pam and Randy Shivak, started a website on Facebook called Solar Activity, and we have 40-some thousand members worldwide who go on there all day long and all night long, depending on where they're at in the world, post images of the sun, and we talk about it. It's a great site. So if you're on Facebook, look up Solar Activity, one word, and that's where you'll find us. So that's enough time about me. I want to talk today about the April 8th, 2024 Great North American eclipse. So as we know, a total solar eclipse occurs when the moon's apparent diameter is slightly larger than the sun's, and it blocks all the direct sunlight. The magnitude of the April 8th total solar eclipse was 1.0566, which is slightly larger than total coverage. What that magnitude means is that the moon's diameter was actually 5.65% larger in diameter from our visual perspective, which is slightly more than total coverage. And that, along with the speed of the motion, is what gives us the length of coverage during the eclipse, or the length of totality. A total eclipse can only occur when the magnitude is 1 or greater, of course. And if the magnitude, visual magnitude, is less than 1, an annular eclipse or a ring of fire will occur, like the one we saw last October. And I viewed from the Peach State Stargaze. That was a lot of fun, being there and observing the eclipse with all the guys and gals there. Of course, totality created by the umbral shadow of the moon only occurs in a limited path across the Earth's surface, with the penumbral portion of the shadow visible over a much larger surrounding region. The maximum width of the umbral shadow band for this eclipse was 123 miles across at its widest, and with an average of about 115 miles wide, which means that totality from any point along the center line would extend about 50 some miles from the center line in either direction, perpendicular to the path of the travel of the shadow. The eclipse's longest duration of totality for this eclipse was 4 minutes and 28 seconds in Nazas, Durango, Mexico. Totality began out in the Pacific Ocean and was visible from 6 Mexican states, 15 of the United States, and 6 Canadian provinces, after which the path entered the Atlantic Ocean, where the shadow lifted off the face of the Earth about 100 miles before reaching Ireland. And the partial phases of this eclipse were visible to some extent, decreasing as we moved away from the center line over almost the entirety of the North American continent. About 6 million people in Mexico lived within the path of totality. 32 million viewers lived in the path in the United States, and another 6 million lived in the path in Canada, for a total of 44 million people who actually lived in the path of totality and were able to enjoy the thrill of just simply walking outside and looking up to view our sun being totally eclipsed. I think that's pretty tremendous. Then if you add people in who traveled to the path of totality, we estimated that another 50 million additional people potentially experienced this total solar eclipse, for a grand total of around 94 million sets of eyeballs peering up at totality on April 8th. Meanwhile, outside the line of totality, an additional approximately 652 million others experienced some degree of the partial eclipse over Mexico, the US, and Canada. This was the first total solar eclipse visible from Mexico since 1991, 33 years ago. It was the first in Canada since 2008, 16 years ago. And it was the first over the United States since, you all know, August 21st, 2017, 7 years ago. My wife Dorothy and I and our friends Pamela and Randy and Kelly Shivak, and some of you may know Sergio Figuera from the Winter Star Party, all opted to go to Fredericksburg to view the eclipse, Fredericksburg, Texas. And that was solely based on climate models. April in Mexico, Canada, or the United States is not really a good time for good, reliable weather, but climate models predicted the best chance to be somewhere around Fredericksburg, Texas. And that's what fueled our choice to go there. Fredericksburg has a population of 11,200 people, and the city's planners prepared for an onslaught of up to 100,000 visitors on total solar eclipse day. That's a 10-fold increase in their population for a couple days. And I don't know what the final numbers actually look like, but I can tell you the day after the eclipse on April 9th, we all went downtown to celebrate and walk around and be tourists and get some dinner. There was no parking anywhere on Main Street. We had to drive a few streets away and walk back to Main Street. The sidewalks, which are like 15 feet wide, were just a seething mass of humanity. It was totally crowded as far as the eye could see up and down Main Street. There was no parking. Every store, every shop, every restaurant was filled to capacity. And excuse me, the waiting lines were long. We've been to Fredericksburg in the past, and normally you're lucky to see 20 people on Main Street. So I think that'll contrast what we experienced that day. We did finally find a restaurant off the main strip, and we still had to stand in line for quite a while for our dinner. But in spite of the crowds and the numbers of people there, everybody seemed lighthearted and happy, even festive. I mean, hey, after all, we just shared an incredible celestial gift. And I think we all basked in the afterglow of the eclipse for days and weeks afterward. It was truly incredible. The state of Texas, with a population of 30 million residents, was predicted to see an additional few million arrive for the total eclipse. And it was much the same, I think, for the other 15 United States where the center line passed. And it made this eclipse a truly relevant event for Mexican people, Canadian people, North American people. But one of the things I found myself asking afterwards, what made this eclipse significant? You know, if you're like me and you've seen other eclipses, every one is totally different and unique unto itself. But yet they're all kind of the same too. I mean, I wouldn't go as far as one guy I know that said, I don't understand why everyone gets so excited about a total eclipse. It gets dark. It gets dark every day. I don't understand what the big deal is. Well, most of us have a little bit more imagination than that, I would like to think. But I think the first thing that made this eclipse significant was the weather. But, you know, all eclipses are affected by weather, and this time was no different. What was different about this apparition was the unusual circumstances that took place in the days leading up to the eclipse. In Texas, climate models had predicted the very best scenarios for viewing weeks out. It was totally predicted to be clear, but then the large weather system began moving in about a week beforehand, and every single day the weather reports got worse and worse and worse. In my native Ohio, I'm from the Cleveland area, like Ken, and in that area, a week out, they said it was going to be raining all day for the eclipse. No doubt about it. It was going to rain. 3 days beforehand, they said 20% chance of rain. 2 days before, they said it's not going to rain, but it's going to be cloudy. The day before, they said Ohio's going to be clear, and it was. So many of my friends from the Cleveland area, yeah, right, Ken. So many of my friends up there got to go out and see it, and almost made me wish that I had gone home to Ohio to see the eclipse instead of staying in Fredericksburg and seeing parts of the eclipse, but mostly clouds. But some parts of Texas were clear. Our friend Sergio Figueroa, who was with us in Fredericksburg, got up that morning and decided, I'm going to drive north as far as I can go before the eclipse starts. And he did, and it was clear where he was at. I know Tim Robinson was several miles away from us, and he had mostly clear skies. Got some great pictures. I wasn't so lucky. Let's see, I kind of lost my space here. Oh, okay. And the lesson therein is that climate models can be useful. And in the 2017 eclipse, they were. Where we went to Smith's Ferry in Idaho, They've been collecting weather data for 150 years, and August 21st in 120 years had never seen a cloudy day. And August 17th of 2017 was no exception. And we had a great eclipse there. But the best plan for eclipse chasers is to be as mobile as possible. Be prepared to travel on the days leading up to the eclipse. Everybody says don't venture out on the roads and the freeways, because if you decide to drive, probably a million other people will too, and the roads are going to be gridlocked. Everyone I talked to said that wasn't the case. People who traveled said the roads were good and clear. So again, climate models are useful, but they're not foolproof. So just be aware of what's going on in the days leading up to the eclipse. The second thing that made this eclipse significant was that this eclipse occurred near the maximum of solar cycle 25. They're predicting the peak of this cycle is going to be sometime later this year or early next year. And the sun has really, really been active. Had this eclipse occurred during solar minimum, kind of like the one in 2017, we may have had a featureless disk with no problems visible. And I think everybody that saw this eclipse can agree that the prominences alone made this eclipse worth seeing. They were incredibly bright, and they were all the way around the limb. And the third thing I think that made this eclipse significant, made it stand out from all the others, was the sheer number of people imaging this eclipse and sharing their images and their impressions and their thoughts on social media. I mean, almost instantly. Hundreds of millions of people viewed this eclipse, and almost every one of them had a smartphone in their hand. And they were using those smartphones and capturing stills and videos and sharing them instantly. The internet was just abuzz with a fevered pitch as people posted images of the diamond ring, Bailey's beads, the corona, the beautiful prominences, just mere seconds after they occurred. And I even saw videos of shadow bands, of crowd reactions. In downtown Fredericksburg, we saw people come out of their homes and gather in their yards a few minutes before totality. Some people were out having barbecues. One family was in the pool observing the eclipse. How cool is that? During totality, we heard car horns sounding. We saw fireworks exploding, bottle rockets whistling as they ascended up into the sky. We heard people hooting and hollering and shouting. We heard guns going off. The last thing I think that made this eclipse significant, at least for us in our location, was the cloudiness. While cameras couldn't really capture a lot of action, our eyes were able to make out very fine details. And also, the clouds made this eclipse extremely dark. Streetlights came on, and the bright glow you see around the horizon during a normal total solar eclipse, I didn't see that this time. The darkness went all the way to the ground. And I think that was attributable to the clouds. So after a few seconds of trying to get good images through the clouds, I realized the futility of my efforts. That just wasn't going to happen. And so I did something I thought I'd never do. I stepped away from my cameras and just stood there next to Dorothy, holding her hand and watching the immensity of the eclipse unfold before my wondering eyes as I fully drank in this incredible experience. In spite of the clouds whizzing by, my eyes were able to capture the tiniest of details that the clouds were preventing the cameras from seeing. And that 4.5 minutes of totality seemed like an eternity. And it seemed like only an instant, all at once. It was terrifying. It was wonderful. It was spiritual, all at the same time. And in that moment, I think I understood the trepidation that our ancient ancestors had to have felt as the sun would suddenly and without warning begin disappearing from view back in those days. And seeing totality with the knowledge of what needs to happen scientifically was another really cool thing. You know, the coincidence of the sun being 60 times larger than the moon from our perspective, while being 60 times further away at the same time. To make this cosmic coincidence occur is just a little overwhelming. Understanding that the mountains and the valleys on the moon are what creates the Bailey's bead, and knowing that parallel light rays get interspersed as they move through our turbulent atmosphere is what creates shadow bands. Makes understanding those things makes the event all the more memorable, I think. And seeing the corona, the corona is just incredible as it stretches out into our solar system, delivering the life-giving light and energy to every living being, is just almost overwhelming. I stood there that day in that shadow, transfixed by the celestial events taking place above and around me and all of our little group and all other people all over the United States. And I think that's a huge part of why eclipses are so popular amongst all peoples of the world. A total solar eclipse of the sun must be experienced to be fully appreciated. Words are just simply lacking. They can't fully explain the feelings someone experiences during totality. And I think it's a personal and unique feeling for each and every one of us. And if you haven't seen a total solar eclipse, there are going to be more opportunities. The next total solar eclipse in the US will be on March 30th, 2023, and it'll pass over Alaska. The next total eclipse in the contiguous US will be on August 23rd of 2044. I've convinced my granddaughter that I'll be too old to drive to Florida for that one, so she may have to give me a ride. The next total eclipse of similar width to this one will be in 2045, and it'll traverse coast to coast in a trajectory similar to the 2017 eclipse, only a little further south. Let's see, there will be an eclipse on October 2nd, 2024. And it will be an annular, and it'll cross over Chile and Argentina. And that's pretty much what I have to say. Before I close, I'd like to encourage everybody that attended the April 8th, 2024 eclipse to go to the aLpo solar eclipse section and submit your images, submit your observations, and share what you witnessed with the whole aLpo community. And while you're there, check out the interesting and unique images and observations that have already been made and submitted for posterity on the aLpo solar eclipse page. And in the coming weeks, I will be setting up some of that and preparing it for the next issue. And we'll be discussing that with Ken shortly. With that, that's all I have to say today. And I'd like to thank everyone for attending and for being a member of aLpo. Thank you very much.
Hey, John.
Yes.
Thank you.
Do you plan on going anywhere to see the August 2026 eclipse?
No.
I'm looking at either Spain or Iceland. I don't know.
I did look. Iceland looks terrible.
Yeah. Well, they're both, it's going to be low on the horizon too.
Yeah. Spain looks like your best choice for that one.
Yeah, it goes right
But-
over Mallorca too, the island.
Yes, I haven't decided yet if we're going to go or not, but it probably not.
Mallorca's at sunset.
Yeah.
There may not even be in Iceland.
Yeah.
Yeah, I think there's one little
Greenland.
spot in Iceland and one little spot in Greenland, and none are close to an airport, and it's going to be a
Right.
real pain to get there.
Hey, John, John, was any of this on a PowerPoint?
No, this was just a text document.
Okay.
But I mean, I could put together a PowerPoint if you'd like.
No, you did good. You did good.
Well, thank you.
John, how many total eclipse did you see?
2 totals. 2 annulars, and I think about 5 partials. And lunar eclipses, I've seen hundreds of them, I think, in my lifetime.
Yeah.
2017 was my first eclipse, and fortunately for us, everything went perfect. It was, if you remember back in 2017, that's when we had all the big fires out in the western part of the United States, and it had been not cloudy, it had been smoggy with smoke from the fires for days. Even the day before the eclipse, the sky was pretty gray, and we were all shocked when we got up on the morning of August 17th, crawled out of the tent and looked up to a beautiful, pristine blue sky. So it was.
Where were you in 2017, John?
We went to Smiths Ferry, Idaho.
Okay. And just to say, Cleveland rocks.
Yes. Thank you, John.
Just saying.
Go, Ken.
You know,
John, do you have a schedule
home-
about the coming eclipses? Like that you could, is it on your website or the eclipse section's website?
I have it on a text document. I'll get it up there soon. I'm kind of waiting for the new website to roll out, and then I can start putting stuff on there. But we
That'd
need
be
to
great. I
talk
think
about that.
a schedule would be really helpful, you know?
Mm-hmm. Okay.
We're looking at getting the website active next Sunday.
Yes.
Just go to Mr. Eclipse and he'll give you tell you when all of the eclipses.
Yes.
Or buy the book. You can get 5,000 years of eclipses.
Yes.
Not only is it there, but NASA.gov has it too, forever.
Yes.
Yeah.
I
Okay.
use all those sites. Yes.
Okay. All right. I want to thank all of you. And John, you've done good. You held our attention without any what they used to call overhead slides. Remember those? You done good. You done very, very good.
Thank
I'm
you, Ken. I
afraid
appreciate
we're
it.
all old enough to remember overhead slides.
Yeah, we do.
Oh, yeah.
X and Y and Z's and L's and S's.
Opaque projectors.
I still have boxes and boxes of those in my closet.
Yeah. Okay. It is now my pleasure to wake up Tony Cook. Tony, what time is it? 9:45 your time. Tony is in Britain. Okay, here's what I have from Tony. He lives, he goes by Tony, but we know him as Anthony Cook, Dr. Anthony Cook. He lives in Newtown in the Principality of Wales, Great Britain. But he is a lecturer in the physics department at, okay, let me try it, Aberystwyth University. How'd I do?
Pretty good.
Pretty good. He discovered astronomy and solar system astronomy after watching or while watching Star Trek, Doctor Who, we all know Doctor Who, the moon landings, and Patrick Moore's Sky at Night television show. I don't know if we ever had the luxury of having that. Did we over here? No. Maybe it's available on downstream.
No, just the magazine.
YouTube.
Just the magazine. He discovered the aLpo when he was invited by our friend, the late Dr. John Westphal, or it was Walter Haas, but it was probably around the 2000s, early 2000s. And I asked him about his own observing activities. He's the director of the British Astronomical Association Lunar section. He's the coordinator of what we call the LTP observing section. They have a different name for it now that he'll mention. And so he's the head of our LTP observing, that's lunar transient phenomena, but in Britain, in the BAA, they've renamed it. He's experimented with shortwave and long-wave infrared observing of the moon and planets. And I asked why the presentation topic is so important. And he says, well, I'm coordinator for public outreach on the upcoming ESA-funded Lunar Meteoroid Impacts Observer Mission, LUMIO, which will look for impact flashes on the far side of the moon. And he wants to encourage astronomers to monitor Earth shine for impacts on the near side of the moon during those times of the month to become sufficiently skilled when they hit the ground running by the time that mission to the moon gets going in 2028. I'm sure we all remember, or some of you remember, that nobody ever really recorded an actual impact of anything on the dark side of the moon, except one, I think it was a doctor in Oklahoma or Kansas in 1953 or 54, and there were all kinds of arguments. Was it a camera lens artifact? Was it a real thing? And it's finally been proven that that guy got it. Now, there are recordings of impacts on the moon quite a bit. Mr. Teskey will attest to that. But in the meantime, it's my pleasure to present for the closing talk for the afternoon, Tony Cook. So Tony, do your thing.
Yeah, I'll just share the screen and hope everything works. Entire screen, let's try that. Share. Okay, and let's get this thing up and running. I'll ask you in a minute if you can see things. It's gone very slow.
The internet cable across the English Sound is just taking too long.
Yeah, it's a long way to the States. My screen is a bit frozen at the moment, which is a bit worrying.
I didn't say, but are you also a member of the BAA, Tony?
Yeah, I just announced that.
You did? I'm sorry.
That's right. Everything's completely frozen on my screen. I'm getting sound from you, but oh, here we go. Slideshow. Let's try to get that working. Modern technology.
You gotta love it.
We're still not seeing your screen, so we won't see the slideshow unless we
I
can
will
see
try to stop
it first.
sharing and do what Wayne did, or try to avoid doing what Wayne did.
It says Tony Cook has started screen sharing, so it's trying.
Okay.
Ah.
Right.
Now presentation mode, or whatever.
PowerPoint not responding.
It's just slow.
Yeah. It'll get working.
There it goes.
That's those damn 300 baud modems. Boy, oh boy.
Yeah. No, I think it's fiber we've got here, so it should be all right.
Dial up.
Right, from beginning. Right. Are you seeing my PowerPoint slides? There we go.
There, along with the sort of an inset at the bottom. It says you are screen sharing. You can see most of it.
Maybe you can drape off the screen. I don't know if you can do that.
It's full screen, but he's got an inset towards the bottom.
Yeah, yeah.
I think we lost him.
Oh no. His image is still there.
Right. Let's try again.
Okay.
Right. Share. Okay. I have a choice. I can either do the entire screen or I can do the application windows of PowerPoint. I will try the latter to see if that works better. Right, let's try to share that. Right, slideshow.
Okay. So we see the stack of them on the left, and then your first slide in the middle there.
Okay.
And the menu bar at the top.
Here we go.
Right. There you go.
There you go.
Right, so I just move everybody down the bottom there.
Everybody hold your breath.
Are you seeing everybody's faces down the bottom like I'm doing, or can you just see the PowerPoint slide?
Yeah.
It's all right. Okay, great. Here we go. So this talk is about lunar impact flashes and an amazing Italian CubeSat mission that will be the first to look for them in close proximity to the moon. Now, the LUMIO mission is due to fly in around about 2027, 2028. And the science team want Earth-based astronomers to monitor for impact flashes on the near side of the moon, compare these with what the spacecrafts are going to see on the far side of the moon to look at the comparison of rates. And we're going to cover today what is a lunar impact flash, the LUMIO mission, the need for near side and far side observations, observing impact flashes from the Earth, and a summary at the end. There's a lot of people involved with this. You've got Fabio Ferrari, LUMIO science team leader, and lots of organizations over in Italy and other countries in Europe involved with this, many scientists and engineers. So, what is a lunar impact flash? Unlike in the Earth's atmosphere, when you get nice, beautiful shooting stars, like we're going to see in August with the Perseids, basically on the moon, because it doesn't have atmosphere, all you get is a very bright, blinding flash. And on the right here, we have a slowed down version, and it's in a loop, so you don't normally see it flashing on and off like this. But this is an impact flash, which I videoed from the UK, first one ever from the UK, a few years ago. It's a bright flash, and that's all you see. So you get if you're actually standing on the moon, what would you see? You see a very bright, blinding flash. Depending on where you are, it could be as bright as the sun. You'd also get a wall of heat coming towards you very quickly. And again, that depends upon how far away you are, how hot it will get. You would suddenly get an excavation of a crater, a great big hole in front of you. You get a localized moonquake, which could possibly knock you off your feet if you're standing nearby, but you probably feel it a kilometer or two away through your space boots. But the most lethal thing of all is, for space missions in the future, is the shrapnel thrown out from an impact, because it travels at many meters and kilometers per second across the surface. And being no atmosphere, this stuff keeps on going in a parabolic trajectory until it hits the ground or goes off into space, basically. So that's the really dangerous part about impact flashes for future exploration. What about the energies involved? They are absolutely huge. I don't know if you can see in front of you, but I have it's not really a paper clip, but it's like a paper clip. It weighs about 1 metric gram, hardly anything. All the impact energies on the moon are derived from this equation. Kinetic energy equals 1/2 mv squared. You've probably done this at high school. Anyway, Just think about it now. If we have a 1 gram object like this paperclip, substitute, and let's say it's traveling at 50 kilometers per second, which is fairly fast from meteor, but not unheard of. That's 50,000 meters per second. If you work out what that is, that's 1.25 megajoules of energy from one of these things. That's enough energy to take one of the heaviest elephants on the Earth's surface and lift it by about 12 meters, which is about 39 feet. So I will just do that now. There you go. The elephant gets lifted up 39 feet into the air from the energy from a paperclip. Now, if the lunar surface gets in the way, that energy is transferred into heat, a crater being excavated instantaneously, ejector thrown out, and seismic waves and a flash of light. Only probably less than 1% of that kinetic energy goes into a flash of light, which we can see from the Earth. Now, I doubt very much if you would see the light from a paperclip, but from objects which are maybe a kilogram in size, yes, you probably would see those from the Earth. The problem is we don't actually know how accurate that 1% is. It might be 0.1%, might be 1%, might be 0.1%. This is something we really don't know terribly well. That's one of the things the LUMIO mission is going to help us to work out. There have been some historical observations. Back in the 1950s and 60s, aLpo, with Walter Haas and so on, had a program to get visual observers to look at the night side of the moon to see if they could detect flashes of light or even streaks, because they didn't know how thick the moon's atmosphere was. It might be, you might get some meteor streaks, but they didn't see any of those. They did see flashes, but they could never confirm them because nobody else was observing at the same time when one observer saw them. Roll on to 1953, and here we have Dr. Leon Stewart, MD, over in Kansas, I believe, and he photographed a flash on the moon. This is a modern-day CCD image which has been degraded, and this is a subtraction showing you what it looks like. We still don't know what that was. It probably was an impact flash. People have looked for the crater, but they have never really confirmed any craters there are from this particular one. Roll on to 1999, and astronomer Armagh Observatory in the north of Ireland predicted that the moon would be hit by lots of linear meteors. Linear meteors have big storms every approximately 33 years. And there were some amateur astronomers in IOTA, the International Occultation Timing Association, who had the right equipment, and they were encouraged to go out and look at the night side of the moon. And here we have flashes which people have seen in different parts of the continental United States. It was also seen in Spain and in Japan as well. That's the first time we had confirmed impact flashes seen. So you'll be pleased to know, and you ought to know anyway, that the aLpo has a lunar impact flash observing program. It's run by Brian Cudnick at the Department of Physics at A&M University, Prairie View, Texas. Here is the existing aLpo lunar meteor impact search page, and there's a mirror site over here at Prairie View University. So I would strongly encourage you after this talk to go and have a look at all the useful advice and suggested times to observe on these websites. Brian Cudnick is an unsung hero astronomer because he started the impact flash work for aLpo, and he is one of the first astronomers who've actually seen with their own eyes impact flashes on the moon, and he commented that they were red. It's like talking to Clyde Tombaugh, the discoverer of Pluto. You've got somebody here who's actually seen the very first bunch of impact flashes, 1999, with his own eyes. So that's another good reason why you should talk to him. He's a legend. Right, let's talk about the LUMIO mission. So it's going to be launched around about 2027, 2028. Goes out of low Earth orbit here, 7 days around there, and on a trajectory to the moon. Takes about 140 days to get there, energy-saving orbit. And it's going to go into an orbit around the Lagrange point, which is a gravitational balancing point on the axis between the Earth and the moon, a little bit beyond. And because it's not just the gravity of the Earth and the moon, but you've got the sun there, the sun gives it a bit of a tug, and it goes into what's called a halo orbit, as you can see around here. And the good thing about that is, although the distance varies from about 35 to 85,000 kilometers, which is, see now, 22 to 53,000 miles. It's going to see the far side of the moon. Now, the moon's going to go through its phases like it does on the near side, but the point is, you don't have to wait for the moon to rise and set. It's going to be always there in the viewpoint of LUMIO, which is going to be quite an advantage. And you're looking at the night side, so there's no earth shine on the night side, no reflected light, so the moon's surface is a lot darker, and it's a lot easier to see impact flashes on a much darker surface. These are the observing opportunities, the ground-based and space-based studies from LUMIO. So from the ground, we can typically see impact flashes between new moon and first quarter, and perhaps a few days beyond, and also on the other side between last quarter or a few days before and new moon. But when it's getting near to new moon, the moon's not above the horizon for very long. It might be above the horizon for an hour. So you don't have long to observe. From the spacecraft, though, it's got all the way from first quarter to new moon and last quarter. And that's 24 hours, 7 days a week. So that's for 2 weeks, it's going to be able to observe impacts on the night side of the moon. The phase will be varying, so the amount of area will change, but it's going to have continuous coverage. Advantages of space-based observing are it can see some sporadic sources that which you can't see so easily from the Earth hitting the moon. And the inverse square law, which I'll talk about in a minute, allows you to see a lot more impact flashes on the moon's surface. Right, here's the camera. It's an interesting little device. It's basically a telephoto lens with chromatic aberration kept to a minimum. It's got a dichroic filter here, which splits the light to the left and straight through. And then there's a camera there and a camera there. And there's two filters. One will look at a wavelength of 450 nanometers, blue light, and one in the infrared at 950 nanometers. All that weighs about 9 kilograms. So it's a pretty clever system. The people involved with this were involved with the DART mission. They didn't have instruments on board the DART mission, but they had a follow-on CubeSat. So when the DART mission hit that moon of that asteroid, and there was a big explosion, a few hours later, the Italian CubeSat came along and took some really cool pictures. So they've had experience, they've had a lot of hardware which works, so they really know what they're doing. So we have a lot of confidence in the heritage of the equipment which is going to be used. Okay, now, as I say again, you've got two filters, one at blue and one at infrared. When an object hits the moon, it heats up. It's basically like heating any lump of material or a star. It's got what we call a black body radiation curve. And the hotter it is, the more it's down at blue wavelengths, as you can see here. The cooler it is, the more it is at red. These have unique mathematical curves. And if you take two measurements, one in the blue and one in the infrared, that precisely defines the curve for a particular temperature. So this thing is going to give us temperature measurements, which is really good. This has already been demonstrated over in Greece with the Nelliota Observatory out there, which was funded by ESA for a while, but they've stopped the funding for that now. And this is a continuation of this, and they will get a lot more observations produced. They're hoping to get anywhere between about 50 and 500 observations per day, depending upon sporadic rates and any meteor showers which are taking place, all due to the inverse square law being closer to the moon's surface. So what's the need for near side and far side observing? Well, you'd expect to actually see a little bit of difference between the near side and the far side, because the far side has slight preferences for sporadic showers than you get on the near side. So they are going to try and prove that. And also because of the Earth's orbital speed around the sun, and also the moon's orbital speed around the Earth, the rate at which meteor showers hits the moon is going to vary, because you've got those velocities added on, depending on which side of the moon these showers hit. So we'd expect to see some differences there. Now, Earth-based impact flash observing has been going on since 1999 with confirmations. Lunar observing is new, so we need to calibrate the two together. Now, you might wonder, how on earth are you going to do this if you've got impacts on the far side, impacts on the near side? Well, you remember that halo orbit, it's not directly behind the moon. They're going to be actually in continuous communication with the Earth. So they're actually going to see a little bit over the limb. And of course, from the Earth, we can see a little bit of the limb as well. So there will be some impact flashes, hopefully, seen both from the Earth and from the spacecraft. That'll be a good way to do some calibration. Okay, observing impact flashes. So from the Earth, it's not such a great rate because we're quite far away. Typically, it's one sporadic seen every 5 to 14 hours, according to the NASA Marshall Space Flight Center, who do a lot of work. In Greece, they got a bigger telescope. They were getting one flash every 2 hours, but they had a huge, big telescope. You should expect to see perhaps one every 10, 20 hours. That doesn't sound great, but if you compare that with finding impacts on Jupiter, you actually have a much better rate of detection with impact flash rates. And of course, amateurs have got a lot more free time. They don't have to put in for research grants to buy time on telescopes. But we do need to train you up to get you into a good sort of state where you can make very valuable observations. Okay, we've talked about when to observe before, so I'll skip that. Equipment needed. Now, what I've got here, you can use smaller telescopes. Don't take this as concrete. You've got to take things bigger than 20 centimeters. I know people who use refractors, and they work very well too, and not as big as 20 centimeters. It's obviously better to have a tracking telescope, but that's not always possible. F5, a small focal ratio, is good because you can capture larger areas of Earthshine and maximize your chance of detecting impact flashes. Ideally, you want to have something running fast, 10 frames per second. 20 or 30 is pretty good. Anything which can capture a 10th magnitude star in a single video frame, you've got the right equipment there. In the past, we've used Watic 902H cameras. You can buy some used one of those for just a few tens of dollars, or modern USB frame capture devices are also pretty good. Optional equipment, you don't need this. I've just mentioned it because some people use it. You could use a GPS clock. Some CCD cameras have GPS built in. Filters can be useful for looking for color measurements and so on. So RGB imaging filters, for example, or Johnson VRI filters can be useful. Some people have even used low resolution diffraction gratings, but you need very bright flash to produce a spectrum. They're like 5th magnitude. When to observe, I've got a website here. This tells you from many different parts of the world when you can observe. If you're not on there, let me know and I'll put up a prediction set for you. And this shows, for example, from New York, Columbia University, on July 28th, 29th, 30th, when to go out and look in the morning to see lovely Earthshine and look for the Zeta Draconids striking the moon. Software to use. Right, so we've got Lunar Scan, which was written by Pete Garral. Was hosted on the NASA Marshall Space Flight Center website, but that link no longer works. But it's a beautiful piece of programming. It's got a predictions here to show you where the impacts are going to occur on the moon. Very useful. You want to maximize your impacts, chances of detecting impact flashes. Talk to Brian Kudnick because he might possibly have the software. He could possibly send you a zip file or send me an email as well. Another bit of software, this is one I wrote. It doesn't have such nice graphics, but it's a lot faster than Lunar Scan. It's called aLpo, and that's available on this website over here. It works like Lunar Scan works with AVI format files. It's pretty fast. A new kid off the block is FDS, flash detection software from ESA-funded Meliota Observatory in Greece. And this will actually work directly on your CCD camera if you can run fire capture on that, and will detect with a plug-in impact flashes in real time. Or you can archive the data just like we have with feed it into aLpo or Lunar Scan. Anyway, there's a website you can look out for that. But beware out there, because there are some nasty little things in the sky which make you think you've detected impact flashes, but they're not. The most nasty one of all are cosmic rays. They are charged particles traveling near the speed of light, which enter the atmosphere, go into a big air shower, and some of these intersect your CCD camera, and you get little dots which look almost exactly like impact flashes, except they're normally very sharp, perhaps just over a few pixels. Real impact flashes are seeing blurred. We also get scintillation causing false detections from mountain peaks and stars, so be careful of those. Science overview. What can be done by looking at impact flashes? The first thing is the time, the date of the impact flash, because if somebody else has seen it with a camera and you've detected it, that confirms it's a real impact flash on the moon if you are geographically separated. The second thing is location. We could do the analysis on the, if once you feed it into aLPho or Lunar scan or FDS, we can do the analysis and get a position out for you. And that could be used by future moon missions to go and look at a recently excavated crater and see maybe it's still got gas coming out, volatiles from the thing. That'd be really exciting. The next most useful thing is the magnitude, and that gives us information on the energy. The light curve can tell us a lot. I'll show you an example in a minute. If you've got people observing in different wavebands, you can get the color. And if you're using a low resolution grating, you maybe get a spectra if you're lucky and get a really bright one. Very, very occasionally, you might expect to see an ejector cloud from a grazing impact on the surface, where it spews stuff out along the line of sight over a few kilometers. That may sometimes happen. There are other cameras out there, a little bit pricey, which can look for heat decay. And lastly, we want to be able to calibrate the LUMIO data. So this is how we locate craters. We use NASA LROC images, and this is one found from a big impact flash seen in Spain. And that's just a few meters across. And you've got ejector rays which go over many, many meters, perhaps even kilometers. That's a good way to find these things. You need images taken under similar illumination conditions. This is the light curve. And it's like a supernova light curve, rapidly up and an exponential decay. But look, we've got little steps on there. What we'd really like to know, are these due to scintillation in our atmosphere, or are these real steps, perhaps due to ejector cloud blocking the light briefly? We need more observations of the same impact to see if these things are true. And a few special cases. Here's one where we have impact flash, which is seen from the UK and Switzerland, and it's elongated. Is this due to, is just by chance due to atmospheric seeing, or was this a glancing below impact? This one was videoed near the moon's terminator, and it's an ejector cloud coming out at many kilometers per second. Some of that material would escape from the moon. And this one is in the shortwave infrared by my PhD student, and it'll last many, many frames. If you shift to longer wavelengths, impacts last a long, long time. So last slide, just to summarize. It's easy to observe impact flashes with a camera capable of recording down to 10th magnitude, at least 10 frames per second. So cameras like an ASI 120mm or use Watic 902H with a video capture USB device would be excellent for that sort of thing. Software to detect the flashes, there's aLPho, you've got the FDS from Greece, or talk to Brian Kudnick, maybe he's got a copy of Lunar scan he can lend you. The LUMIO mission will launch in 2027, 2028, and will be a great opportunity for amateurs to contribute to science by helping calibrate near-side and far-side impact flash observations. Maybe some of the new craters you discover will be visited by rovers in the future, who knows? Okay, where to look on the moon? We've got a website here, when to look. And please, please get in contact with Brian Kudnick, because he's got all the information you need to know to get you started on observing impact flashes on the moon. And last of all, I want to promote his book. A little bit old now, but it's very, very relevant. Lunar Meteoroid Impacts and How to Observe Them. There are no other books out there with a title like that. That's the only one written about lunar impact flashes. You might want to have a look at that. So it's very, very, very useful. Okay, thank you for your time. Are there any questions at all?
Seems like it would be very useful to have several telescopes. 8-inch Schmidt-Cassegrains are relatively cheap on the used market right now. Have several of those set up with different filters, observing simultaneously.
Absolutely, yeah. One thing I forgot to say is it would be very useful to occasionally go over the stars and their magnitude and their color indexes to get to calibrate the camera before going back onto the moon, and do that maybe every 5 or 10 minutes, just so that if you do see a flash, you can get the very good handle on the magnitude. The other thing I forgot to say is, even if you don't detect any flashes, please, please send Brian or myself dates and the start and the end time of your video, because we need to know when flashes are not seen. because that's vital information for working out the rates of impact on the moon.
And don't throw away the observations.
Sorry?
And don't throw away the observations.
Don't throw away the observations. And if you get an occultation, well, that's great as well, because if you've got a high-speed camera, you can learn something. If it's a double star, or that can be quite useful too.
But the tendency, if you didn't see anything, is to throw away the observations rather than keep them on the hard disk.
Yeah, I personally keep all my video, but some people may not be able to afford too much hard drive space. So if you run it through 2 or 3 of those programs that detects nothing, we would obviously like to know the start and the end times, and we would love you to keep your video in case software improves, so we could, or somebody detects something, we can get you to go back and look at that particular frame at a particular time. But we realize people have to be practical if they don't have enough hard drive space.
Hey, Tony.
Tony, have you seen any correlation, like when there's meteor showers at the same time?
Yeah, there's a lot more impact flashes being detected. When I did the Leonids I didn't do the 1999 one, but I did think it was 2001. I detected flashes then, and they were also seen from different parts of the United States at the same time. And I was perched on a balcony of a colleague. I worked at the National Air and Space Museum, and she let me use a balcony because I had a beautiful view of the western horizon. I followed the moon all the way down pretty much to the horizon. There was even a crane in the background in the end, and I got 2 impact flashes that way.
Tony, this is Roger Venable, and I don't know if you're aware, but I used to be very interested in this area of research. And in the 1999, I hope I have the year right, the meteor storm of the Leonids, the peak was predicted to occur in Europe, but from my location in North America, I had a look, not at the time of the peak, looking at the moon, and I was looking visually, and I estimated that I saw 4 flashes per minute on the dark side of the moon using a 16-inch telescope.
Wow.
The next time, and I reported this to the aLpo TLP coordinator, who I don't think was you at the time. I've forgotten his name. And I also wrote a letter to the International Meteor Organization, and that was published in their letters to the editor.
Yep.
But what discouraged me from making further observations was the difficulty of processing the videos. And I'm delighted to see that you've got a new program. For me, I stopped observing these because the difficulty, it's extremely laborious and even difficult to prove that you have something when you do it manually. And so I just want to call people's attention to the idea that if you plan to do this and record them, you must have software to process the videos.
That's
we observed that same Leonid meteor shower with a lunar coronagraph on Mount Lemmon and reported, we didn't see anything. We reported the results in Icarus.
Wow.
I
I'll
have
to look that up.
hours of video of the dark side of the moon from the next year. I think it was the Perseids, and there was a Perseid meteor outburst, I think maybe a year later or something. And I have hours of video for it, and I've never been able to process it.
Okay, we'll have a go with Alfie, and FTS has got an archive mode where you can upload some data. I can't promise it won't be arduous, but with computers being faster now, it shouldn't take so long as it used to.
Hey, Tony, I'd like to know if there's a way you can condense this to even a full-length article for the aLpo journal. And as far as the deadline goes, why don't we use sometime in October?
Okay, sounds good. I need to encourage a lot more people to participate.
Yeah.
We've got to train people up in different parts of the world, not just continental, in the Americas, but also in Asia and other parts of the world. Because if you just have it in one area, you see the moon only over a certain range of phases at a certain time. But around the world, you get more towards a 24-hour coverage. There will be gaps in the Atlantic Ocean because there's not much land mass there. But over the rest of the world, there's always a bit of land mass around. So that would really help supplement LUMIO observations.
Rich, and that brings up, I want to repeat what I said yesterday. There's a cell phone app for, well, it's on my iPhone. It's called Moon Calendar.
All right. Yes.
And it's good for at least planning your observing sessions. It's, you know, I use it. It's got some great graphics. Let me see here. Moon Calendar. Okay, here's, let me see, here's the, that's what you get, the opening screen. Shows you what's what. Then you have a calendar function that shows you for the current month, every day for the current month. Then you can advance or regress or whatever. You can set the location. You know, it's a great thing to have to help you plan when you will be able to get out.
Yeah,
and do that. And let's see, there, I thought there was something else. Oh, what the aLpo still calls the Lunar Transient Phenomena program. It's been renamed. What is the BAA now called that same program?
Well, for a long time on this side of the Atlantic, we had transient lunar phenomena. In the United States and Canada, we had lunar LTP.
Yeah, but you had another name. There was
I call it lunar geological change because
that was it. That was it. Lunar geologic something. Yeah.
Lunar geological change, because for a while we were looking at NASA LROC images trying to detect changes there. It proved extremely difficult to do, so we gave up on that, but the name is stuck for the moment.
Okay. And then there's also the Hidden Craters research program that you're running too.
That's right, buried craters and basins, yes, because if you're trying to study the geology of the moon, you really need to know where all the craters are, because if one crater's on top of another, then it's younger. But there's a lot of craters we can't see because they've been buried by craters. But under the right illumination, we can just about make out the rims or parts of the rims and deduce there's a crater underneath. And the same with impact basins as well.
Great.
I got interested in the latter at the Air and Space Museum because I worked on Clementine data there, looking at stereo images. It took about 2 million images, and I processed those and was able to produce a checkerboard pattern of the moon's height. It had gaps in it, but from that you could work out there were basins we didn't know about. And that got me into basins, and I'm still looking for new ones based upon the LROC data we have now, which is much, much better.
When will you be back in the States, if at all?
I don't know at the moment. I haven't traveled to the States for years. I'd love to come again sometime.
Okay. Tim, do you have anything to add before we wrap up today? Before the talk, before the keynote tonight?
No, but I just want to thank all the presenters for making this a very successful conference. Couldn't have done it without all of you. So thank you very much. And I will be sending out the link for the meeting later in about a half hour.
Everybody pay attention to your email box to get that hyperlink, because you're going to need that to log in for the award presentations and the keynote speech by Bob Garfinkel. Thank you all for being here today.
Great job, everybody.
Thanks.
Good night, Tony.
Are you still there?
I'm still here.
Right. Okay. Good night. See you later.
Good night.
Take care.
I'll see you guys
Tony?
later.
Nice conference, guys.
Hey, Tim, this is Wayne Bailey.
Yeah, Wayne.
Hi, Wayne.
Are the talks going to be available anywhere, the copies of the PowerPoints or anything like that?
The talks they're on YouTube.
Okay, or the videos are.
The video, yeah. I don't have any of the talks, PowerPoints or anything like that.
Okay, thanks.
Yep, yesterday's is on now, and today's, well, we've live streamed it over there, so it's there now too.
Thanks.
All right.
You said that before. I should have thought of that.
No worries.